Excellent. Okay. Thank you very much for attending. Welcome to this training session on, I'm trying to click through on the slides and it's not working. There we go. Welcome to this training session, Introduction to Using Firedrake on ARCHER2. So there's 4 demonstrators. There's Jack Betteridge, Koki Sagiyama, myself, Joe Wallwork, and also David Ham. So Jack, Koki, and I are all postdocs who do research on using Firedrake on HPC. And David is the project leader of Firedrake. So we'll be here to answer your questions and to run the demonstrations today. So the objectives, as you'll have seen in the advertisement and the emails that you've got, are to be able to write a weak form of a PDE in the unified form language, which we'll talk about quite a lot. Solve a range of different PDEs using Firedrake, so linear PDEs, non-linear PDEs, time-dependent ones. Configure solvers and preconditioners for HPC. And then finally, the bit that everyone I imagine is looking forward to is running Firedrake in a HPC environment on ARCHER2. So hopefully you've all been able to connect to ARCHER2 and to the cloud server. But if you haven't, then please feel free to send a message in the chat and someone will try and help you. So just the 101 for those of you who are new to the finite element method, a very brief introduction is that we take your favorite PDE. So in this case, we've got a steady state PDE and some Dirichlet conditions, some Neumann conditions, and we solve it in a weak sense. So the aim here, this is for a linear problem that I've presented it. We're searching for weak solutions in a function space which satisfy the equation below. So we have bilinear form on the left-hand side and a linear form on the right-hand side. So we'll go into a lot more detail of what all this means during the demos. But given that we choose a discrete subspace of the function space that the solution lives in, which has a basis with finite support on the domain. And then we discretize both the domain and the functions using a mesh. When you have this integral on the left-hand side at the top of some function with a test function over the domain, we can split it up as integrals over each element of the mesh. So for example, it could be a 2D triangular mesh. So it's a sum over all the triangles. And then since we've assumed a particular form for the function space, for example, it could be polynomial on each element, we can perform quadrature in an exact sense on each element in order to do these integrals. And using this weak formulation, we have an integral equation, and we can then solve the linear systems which arise from this approach. And at the end of the day, as Firedrake users, it's mostly up to us just to choose the mesh. So there's lots of different ways that we could choose that. The function space, which is appropriate for the problem at hand, and then all of the details of the linear solver, the nonlinear solver, preconditioning, which we'll look into quite a bit for the HPC case, because it becomes quite important at large scales. And a brief introduction to Firedrake. So Firedrake builds upon the domain-specific languages developed in the Phoenix project, which you may well have heard of. Like the Phoenix project, it uses the unified form language. So the idea is that it's a very high-level symbolic representation of the finite element problem, which is, if you understand the maths, then it's very intuitive. But then underneath the hood, Firedrake is generating C code, which is very efficient using PETC. And so it's kind of, it's very easy for application scientists and mathematicians to use, and yet it's quite a powerful approach, which leverages the software which PETC provides. Firedrake also inherits PETC's unstructured mesh data structure, which is one of the main differences with Phoenix. And thanks to the coupling with PETC, Firedrake allows for a very concise and flexible solve call. So here we have a solve which has the bilinear form equals the linear form. There's a solution U, and then the solver parameters are configured at runtime. So this can be very, very flexible, and we'll see lots of cases where you can customize the solver parameters quite extensively. I won't go into all the details of this workflow here, but this is just a sort of very high-level overview of how Firedrake works. So if we start at the top with the picture of the dragon of Firedrake, the mathematician or the application scientist writes the problem in UFL, as in Phoenix. And then the form compiler turns this symbolic code into the tensor contractions on this PyOP2 level, just below it. PyOP2 is the interface, which then interfaces with PETSI, as you can see on the right-hand side. So that's telling PETSI what to do with regards to the low-level linear and nonlinear solves. PyOP2 also interfaces with Loopy, which handles the parallelism. And then you can see, sorry, I missed something out near the start. If you look on the right-hand side, near the top, we've got fiat and finite. Those are the, that we use those when we're doing the form compiling. So fiat is shared with Phoenix, whereas finite is not. And then finally, in the top right corner, there's some outer loop processes that can be done to do optimization and sensitivity analysis using Dolphin adjoint and its automatic differentiation engine, PyAdjoint. So we can come back to any questions anyone has in a couple of minutes. But that's a general overview of Firedrake. Firedrake also has a number of different application codes. Here's 4 notable ones. So FireShape is an optimization toolkit, shape optimization toolkit for Firedrake. Feel free to browse these websites and take a look at the results. We've also got, there's a coastal ocean and estuarine modeling toolkit called Thetis, an atmospheric modeling toolkit called Gusto, and then IcePack is an application code that does ice sheet and glacier flow modeling. There's a couple of examples at the bottom there from Thetis and IcePack. And so this is the order of proceedings for today. So following this introduction, we're going to look at 2 of the notebooks on the notebook server, which hopefully you've been able to connect to. So there's a modified Helmholtz problem, Poisson problem. Hopefully that will take us up to 2:10, where we'll have a break. And we'll come back at 2:30 for another 2 notebook examples given by the demonstrators, so linear elasticity and the Burger's equation. We'll have another break at 3:20 until 3:40, where we'll return to the Poisson problem and look more into these solver parameters that I was referring to. And then finally, the bit that everyone is waiting for, from 4 o'clock until 5 o'clock, we'll have time to do the extension of all this notebook work onto HPC. So we've got a few minutes just to take any brief questions. There'll be lots of opportunity to ask questions throughout the whole workshop, but if anyone has a question now, if you could put up your hand or put it in the chat, then that would be great. Thank you. Oh, we've got a question here. Does the fact that you use OP2 mean that you can run on GPUs in principle?
Shall I answer that? So we don't use OP2, we use PyOP2, which is a different implementation of a similar idea. OP2 is completely statically compile time, whereas PyOP2 is a completely runtime system. There is a PhD student at UIUC who is doing Firedrake on GPU stuff. This has actually been done a few times, and it always gets to the point where someone can assemble one forms on GPU, so do an actual integral on a GPU, and then they stumble into the fact that solvers on GPUs are hard. But actually, in the last, say, 2 or 3 years, we've got to the point where Firedrake has very good matrix-free solver support. So if you have one form assembly and matrix-free solvers, then you could, in principle, have a proper implicit GPU solution. But no one's put those building blocks together. It's one of the things I'm hoping to do in the next couple of years if we can make that happen and resource it.
Okay, we've got a response. Thanks. The final ARCHER2 will only have a small AMD GPU partition, but I was just asking for interest. Is there any further questions, or are we happy to proceed?
I will add in that while we don't have GPU support, some work that was basically started with GPUs in mind does mean that we have really quite good vectorization support, which is obviously important on more or less any modern processor. Why don't you go for it, Joe?
Cool. So hopefully you can still see my screen. So we're now moving away from the presentation and onto the notebook server. So hopefully you will have arrived at something like this. Feel free to click through the notebook as we do it, if you find that useful. But I'm just going to share my screen, run through the first part of the tutorial. We'll have a couple of exercises, and then we'll progress on to the later tutorials. So the first one is SPD Helmholtz. So I should probably zoom in because I don't think that's that big. Does that look okay for everyone? Yeah. Okay, so as I said, we're going to be solving a modified Helmholtz equation. So you'll notice that there's a negative sign in front of the Laplacian here. That ensures that the stiffness matrix that we're going to form is symmetric positive definite. So it's going to be easier to solve than if it wasn't modified.
Has Joe just frozen for other people?
Yeah.
Oh dear. I'm just going to message him on Slack.
Hello, can you hear me now?
Yeah, now you're back.
Okay.
Oh, and you're gone again.
Hello?
And now you're back again. Is something, do you know what's going wrong or?
Yes, I just moved the internet box out of the cupboard. Hopefully that helps.
Okay. No, it doesn't because you've frozen again. Okay, should we shift this around so someone else runs this one and we hand back? Or yeah, so he's just stopped sharing. Shall I? Oh, I've got all the cloud monitoring stuff up. Jack, do you want to run positive definite Helmholtz?
Yep, I can take over from that. Let me just load it up and share my screen. Right, can you see the screen?
Yeah, we're all good.
And it's big enough, hopefully, as well for everyone to see it.
Sorry, Jack, can you hear me now?
Yeah, I can hear you now.
I'm happy to narrate it if you want. Or
yeah, if you want. Yeah, no, I'll just share the screen.
Yeah, sorry about that. Thanks very much for taking over, Jack.
Joe, we've just lost you again.
Oh dear. I'll carry on.
Yeah, carry on, Jack.
So yeah, as Joe was just saying, we've got the negative sign in front of the Laplace operator to make sure we've got a symmetric positive definite operator. So we've got our sort of strong form of our PDE here, and the domain we're going to solve on is a unit square. And the f on the right hand side is some known function. And we're also going to prescribe some Neumann boundary conditions. So this is the grad u dot n, which is the normal, is 0. And so in the standard way for the finite element method, so we'll go slowly over this to start with if you haven't seen it before. We're going to write this as a weak form. So we take the original strong form of the equation, and Zoom has decided it's going to tell me lots of information. We multiply the strong form of the equation by a test function, and then we integrate over the domain of interest. So that's what you see here. And once we've done that, we've also integrated by parts here to move the derivative, the second derivative on the u to be a first derivative on the u and the first derivative on the test function v. So this is the weak form of the equation, and this is what we work with at the UFL level. And you can see with the note below shows that the boundary condition that we have above, so this is the grad u dot n is 0, is weakly enforced by removing the final term in this equation. And we're going to use, as it says here, a H1 conforming method. So the full problem is as follows. So we're finding a u in a desired finite element space such that this equation here holds. We're also prescribing, as you'll see many times throughout this workshop, prescribing the right-hand side function f to be this expression here, so that we obtain an analytic solution that we can compare to. Right, so I'm just going to press straight on to the code now. So as you'll see at the start of almost every Firedrake script, the first thing we'll do is import everything from Firedrake module. So this should just run here. So from Firedrake, I want to import, oh, and that I've got a warning there that I shouldn't see. This is because I'm running locally. Hopefully you won't see this warning. But we import everything from Firedrake, and what we want is a unit square mesh, and this will allow us to construct the domain in which we want to solve the PDE. Now, Firedrake is fully documented, so if you want help on any inbuilt functionality of Firedrake, you can type help and the name of the object or the function, and you will see output as you do here. And we also have the delights of running in a notebook. So actually, if you use some notebook magic and you type a question mark before the object or function of interest and execute it, you'll get a little pop-up window like you're hopefully seeing on my screen with the information. So you can see the parameters you need to put in, the number of cells in the X direction, number of cells in the Y direction, and all sorts of other keyword arguments that you can supply. I'm going to have to move the Zoom window around so you can see what I'm doing. Right. So for this problem, we'll define a unit square mesh, which is 10 cells by 10 cells. You need to remember to execute the cells, otherwise we won't see anything. And Firedrake also has built-in plotting functionality that can actually show you what the mesh you've just generated looks like. So if you look at the code in this cell, we can make a call to tryplot, which mimics the matplotlib function tryplot, and it will show us what this mesh looks like.
Jack, you failed to run the first cell.
Yes, this is a terrible mistake that I've made there, is I forgot to run the I think David was waiting to he spotted that I hadn't done that. Here we go. So hopefully you can see a 10 by 10 triangulated mesh over the unit square. And the boundaries have been highlighted in different colors. These correspond to the different boundary labels that are mentioned in the comment. Right, so now that we've defined our mesh, we can go ahead and define a function space on that. So we want a H1 conforming method. So we do this by calling the Firedrake function space. The first argument is the mesh we've just generated. The second argument is the type of finite element. So in this case, we want CG, some conforming finite element. And the final argument is the degree. So here we want degree 1 conforming finite element. So we get no output from that function, but we've defined our function space V. Now we want to create symbolic objects which correspond to the test and trial functions. And in Firedrake, these are, as you see, defined by calling test and trial function with the argument of the function space passed in. So define those just as we saw in the mathematical weak form we saw right at the top. We'll call those U and V. So executing that cell, those symbolic quantities are now defined. If we want to define our function f that lives on the right-hand side of our PDE, we're going to need access to the spatial coordinates x and y. This is done by calling the Firedrake function spatial coordinate, providing the mesh, and that spits out the components of the spatial coordinates. So in this case, we've got a 2D domain, so we get an x coordinate and a y coordinate, and we can use those to define the function f as you saw above. So it's 1 plus 8 pi squared times cosine the product of cosines. So define that there. And then finally, we get on to defining the weak form itself. So we define our bilinear form A, and you can see we can just call these UFL functions to get the symbols we see in the PDE above. So we've got grad V and grad U, and we're taking the dot product of those, and then we're adding on the product of U and V, and we're integrating over the domain. So we do that by multiplying by this dx. And the right-hand side, the linear functional, is defined as f times v. So if we just quickly scroll back up, you can see it very much corresponds to this expression and the mathematical expression above. So I'll nip back down and execute that cell. Oh, too far. There we go. So now we've defined everything we need to express our PDE. So we're going to define a function now on our function space V. So this is UH, which will hold our numerical solution to the PDE by using the Firedrake function, which creates a function object to store the solution in. And finally, we make a call to solve, which will solve the PDE A, the bilinear form equals L. And notice we've used a double equals here to enforce equality. This is part of the limitation of the expressive nature of UFL. So we have to use a double equals here, not as equals as assignment in Python. So that expression, the first thing that goes in is the PDE that we want to solve. The second argument is UH, the function object we've defined that we want to solve into. And finally, we pass in some solver parameters. So this just tells us that we want, we're telling PETSI that we want to use the conjugate gradient Krylov subspace solver to solve that problem. And if we execute that cell, it goes away for a second and solves the problem. And to prove that we've actually gone away and solved that, we can use the inbuilt trip color plotting function, which again mimics the matplotlib functionality, and we can visualize our solution. So you can see here in the notebook, we have this pattern, which is the solution to the PDE defined above. What's more, since we've have an exact solutions, we've got an analytic solution because we chose our f accordingly, we can actually in Firedrake define another UFL object, so this uExact, which is the exact solution, and we can calculate the error that we made in solving that PDE and plot that, again using the trip color matplotlib functionality. So you can see here the error is highest in the opposing corners. Right, so that was possibly a bit fast, but that means there's plenty of time to go over the exercises. So there are two exercises at, oh, hang on, there's more afterwards. So have a go at these two exercises. So in the first exercise, you use a higher polynomial degree for your function space. And the second one, you can use a quadrilateral mesh. So don't forget, you can call the help function on the mesh to see the different keyword options. And there's another exercise beneath that that looks at the convergence of the method. Feel free to ask any questions if you get stuck on anything. And if you find these exercises really easy, feel free to have a sneaky peek at the next section. All right. There are also breakout rooms. If your question isn't being answered, feel free to pop into one of those breakout rooms and someone there will help. I'm going to stop sharing my screen now.
So David Hensey's asked if I have piecewise Dirichlet, if I have Dirichlet conditions, how do I specify them? You will see that. We'll get to those. But the answer is that you specify Dirichlet boundary conditions to the solve. And because in the finite element method, what is happening is that you are effectively changing the solution function space to take account of the strongly enforced conditions. whereas weakly enforced conditions form part of the bilinear form. So that's a distinction that's in the maths that's then therefore reflected directly in the way the code works. We'll probably give about 5 or 6 minutes for people to play with these numbers.
Yeah, and we're keeping an eye out on the breakout room. So if you want to join one of those, if you've got any problems, we'll just hop in there.
I should say, if you have Firedrake problems, please don't drop into one of the EPCC people's breakout rooms, because they probably won't be able to help you. What's the major clear difference between Firedrake and Phoenix? So the answer to that question is that at the surface level, they look very similar because they both use UFL. The way that you specify solvers is slightly different because Firedrake is much more tightly integrated with PETSI than Phoenix is. The big difference is under the hood. So basically, Phoenix is a C++ library called Dolphin, or these days Dolphin X, which for which just the kernels that integrate over a single cell or a single facet are plugged in, whereas Firedrake is essentially a pure Python layer sitting on top of PETSI, which is C, and everything is generated. So in Phoenix, somewhere inside Phoenix, there is a pre-written out C++ loop over all of the elements, whereas in Firedrake, that loop gets generated for each case as you do it, which means, for example, in Firedrake, that loop will be strip mined for the vector length, and Firedrake will assemble a number of cells at a time, which is equal to the vector length of your processor, because we can rearrange much more of the loop than is possible in Phoenix. So no, CG in that line stands for continuous Galerkin. Yeah, when we live in finite element world, we kind of live on the edge of two nomenclatures. So the nomenclature that people in finite element land use for discretizations is different from the nomenclature that people use for solvers. And so CG in finite element land is a term which is essentially synonymous with P, if you know that one. So it's the scalar continuous polynomials of degree, in this case 1. The number at the end is the polynomial degree. When Jack set the KSP type to CG, that really did mean conjugate gradient. That's because that's in there. So what happens inside the curly brackets of the solver options, you're actually directly talking to PETSI. So effectively, that's a different programming language in there. It's the PETSI language for programming solvers, which is different from the UFL embedded in Python, which exists outside those curly brackets. Yes, you're right, David. There is a built-in tolerance, both a built-in relative and absolute tolerance, although the default absolute tolerance is, I think, 10 to the minus 50, so you'll never hit it. So effectively, it's, I think, 10 to the minus 7 relative tolerance is the default in PETSI. But you'll see this a little bit later. As soon as you get into any problem that isn't very easy, then you have to start worrying about what those tolerances are, and you have to set them. It's unlikely to be the case that a default will work for you. That's right. You're exactly correct. In fact, it's even more complicated than that, because you have to ask the relative tolerance on what, and you probably want it to be the relative tolerance on the preconditioned norm, which you can do. Amin Raffaelli asks, is it possible to tell a little bit more about CG? What would you like to know about CG? What's the difference between Q and CG on quad meshes? Nothing is the difference between Q and CG. CG means Q. You do need to be careful in DG, and in fact, if you ask for DG on quads, Firedrake will warn you, because there are two discontinuous spaces on quads. There's DQ and DP. So DP is polynomials of degree n, and DQ is in bilinear or in 3D trilinear polynomials. And you need to say which one you mean. So one of the things about Firedrake is we can't magic away mathematical decisions for you. We can magic away the implementation, but you have to tell us mathematically what you wanted. Does Firedrake, so Firedrake doesn't itself provide a hook into TS, which is the Petsy time stepper. Some people have done it. It's possible. It's not that hard to roll your own. Most people code their own Firedrake time step solvers. However, there is now something called, someone remind me, begins with an I.
ARCHER2.
ARCHER2, thank you. ARCHER2 is a library led by Rob Kirby at Baylor, who's the same guy who originally wrote Fiat, which is a time stepper library that wraps around Firedrake. And so possibly as long as your time stepper is sufficiently standard that it fits their world, ARCHER2 is probably a good place to go. Shall we proceed onwards?
Yes, I can resume sharing my screen. So hopefully everyone had a chance to have a go at those exercises. There are some hints there. If you haven't managed, should I go over briefly what the solutions are here, or should I move on?
We're kind of okay for time. Why don't you do 1A and show people how to do that?
Yep. Okay. So so if we take a look at the where we defined our function space above, oh, too far. You see, we use this function space to create the function space. So since we're working in a notebook, everything that's defined above is still available to us. So let's say we want a new function space. Let's call it W. You can say that's equal to function space. So we still have our 10 by 10 mesh called mesh. We still want conforming finite elements, so CG, and the final argument to that is 2, right? That gives us our quadratic, piecewise quadratic approximation. And if you didn't know that, the way you could find out, if I open a new cell below, I can actually type help on the function space. Class, and execute that, and it will tell me all about the arguments that you have to put into the function space. I won't go through solving the problem again, but the procedure is exactly the same. You just replace everywhere you see the capital V in all the example code above with the capital W I've defined here. So you can add some more cells and have a go at that if you haven't had a chance. Right. So there we go. Right. So part 2, we're going to deal with inhomogeneous Neumann conditions. So here is the problem we saw above, this modified Helmholtz. And now what we're going to do is we're going to prescribe some Neumann conditions that are not 0. So we've got on some boundary, we're going to say that the Neumann condition is equal to G, which is a constant, which is 1 on the boundary gamma 1. And then everywhere else on the boundary, we're going to have homogeneous Neumann conditions. And then the boundary where we're setting the boundary conditions to 1 is going to be the line x is 0. Right, so previously you saw the weak form of the PDE, and we could just eliminate the final term because it was 0 everywhere. Now we split the boundary integral into 2 parts, so one over the whole boundary excluding gamma 1, and another part which is the integral over the boundary that is gamma 1. The boundary, the term that is over the boundary excluding gamma 1 disappears because that's just 0. But then we want to see how to set the value on the line x is 0. So to do this, we take a look again at the help for the unit square mesh. So I'm going to actually put the help function here so it stays up. But you can use the notebook magic if you prefer. And you can see at the bottom here, it defines the 4 boundary labels for the unit square domain. So the one we're interested in is the plane x is 0. So that's our gamma sub 1. And that is given the label 1. So again, what we're going to do is we're going to create our mesh, our function space, our test function, our trial function, and set up the function f and the bilinear form a. So that's all done in this cell here. And to prescribe the inhomogeneous boundary conditions, we're going to define a new function. And this function is a constant function. So we can use the UFL constant, and the argument provided to that is the value of the constant that you want the function to be. So this makes a function called g, which is just constant everywhere and takes the value 1. And then our linear functional L is the previous term we had, the f times v integrated over the domain, the interior of the domain. So we do that with the dx. And the boundary term is our constant function g times the test function. And now we replace the measure with the with ds, and the 1 is this corresponds to the label we saw above. So the plane x is 0, and that performs an integral over the boundary, but only over the part we've prescribed. So this gamma 1. Did I execute that cell? Yes. So I'll execute this one. So finally, we again define a function to hold our solution, UH, and we call a solve again with the conjugate gradient solver as we did before. And of course, the final bit is left as an exercise. So if you've been following along with this in the notebook, you should know hopefully how to plot that that solution. I'll give you a couple of minutes to quickly do that, and then whilst I retrace the steps and find the solution. So a couple of minutes to try and plot the solution. Let us know if you have any trouble.
Min has his hand up.
Oh, yep. Feel free to either unmute yourself or ask in the chat if you don't want to do that.
Oh, hand down.
Hand down. I don't know if that was a false positive or you're going to ask. That might have been a misclick, but if you do have a question, I mean, feel free to ask either in the chat or a breakout room. I'm going to solve the exercise whilst my screen's hidden, so you've got a chance.
Here's one I made earlier.
We've got a question in the chat. Where was it that we specified gamma 1?
So we didn't. So if you take a look, let me scroll away from the solution and then I'll share my screen again. So if you look at their help for the mesh here, for the unit square mesh, we're provided with a list of labels which are the boundary of the unit square. So we didn't define gamma 1. So gamma 1 is one of the predefined boundaries of the unit square. So we just specified that here when we did our integration, our linear functional. So because we're doing the surface integral, which is the ds, or the boundary integral ds, the argument to ds tells you which part of the boundary you want to perform the integral over. So if we provide 1 here, that means just over the plane x is 0, or the line x is 0 in 2D. If you want to see help on that, I don't know how messy this will be in the notebook, but you can, if you want help on ds, you can just type help ds, and that will tell you lots of information. So this is the
so if you used a if you didn't want our predefined sides numbering, what you would probably do is just load a mesh from a mesh generator. Many Firedrake users use Gmesh because it's good and free, and those mesh generators typically enable you to paint the boundaries however you like with numbers, and Firedrake will read those in and use them. Steve Bembo also says, how could I confirm that grad u.1 is 1 on gamma 1 in the solution? So, well, what you could do is you could compute the integral grad u.n minus 1 times ds and assemble that, and it should be a good approximation to 0. That's the so it is possible, we won't go into this here, it is possible to point evaluate solutions, but actually in the finite element method you usually don't want to do that, not least on a boundary where the finite element solutions have a very weak or undefined value. So it's usually in the finite element method, what you want to do is if you wish to test something about a solution, it's best to think of an integral quantity that would tell you what that solution would be. Shall we dive forward? Because it's
yes, I was going to say, so I've got quickly here, so that's my solution I was preparing whilst my screen was hidden. So it's exactly the same as the way you did it above, and you can see the solution plotted there. So feel free to ask if you had any issues there. So I'm going to hand over now to Koki, who's going to go through Dirichlet boundary conditions, I think. Oh no, sorry. Yeah.
Yep.
Over to you, Koki.
Can you stop sharing? Yeah.
Yep.
Share screen. Okay, I hope you can see the screen now.
Yeah, we've got you. Maybe
Okay.
blow up slightly. It's pretty good actually. It's all right. Yeah, thanks.
Okay. So we take a look at the Helmholtz equation, and we now want to take a look at Poisson problem. Unlike the Helmholtz problem, we need to apply Dirichlet boundary condition to have Poisson problem well posed. So this is our Poisson equation. We are solving for U. This is the solution, and F is the body force term. And we are applying Dirichlet boundary condition U equals G on some part of the boundary, and on the rest of the boundary, we have Neumann boundary condition. And the Neumann boundary condition is imposed weakly by appropriately including the boundary integral terms, while the Dirichlet boundary condition is applied strongly by modifying the function space on which the solution is defined. So here, V is a function space from which U, the solution is drawn, and we have two modified function spaces, Vd and V0. And Vd is a space for functions that satisfy Dirichlet boundary condition. So this is the space for solution. And V0 is a space of functions that are 0 wherever we have Dirichlet boundary condition. So this is the space for test function. So test function is basically perturbation from the solution, and the solution plus perturbation has to satisfy this boundary condition. And we know that the solution satisfies this boundary condition, so the perturbation has to be 0 wherever we have this boundary condition. So this is our strong form. We apply the test function to this strong form and integrate it over and apply divergence theorem. We have our weak form, grad u dot grad b, and we also get some boundary term with which we can apply Neumann boundary condition, if any. And here's our body force term. This is very straightforward. And this equation has to hold for all v living in V0. So this is the setting. But in Firedrake, as already mentioned, we do not directly define these modified function spaces. We always work with the full unmodified function space P. And we use dirichlet BC object to handle the function space modification. So let's do some setup. As before, we import Firedrake, and we again use unit square mesh. This time, 10 elements in each direction. And we define CG1 function space on this unit square mesh. Let's talk a bit more about the problem. We are solving solving the Poisson problem on unit square. We have already defined, and we have dirichlet boundary condition, the homogeneous dirichlet boundary condition all over the boundary. So there's no Neumann boundary condition. So we don't have to worry about this term because gamma n is empty. And finally, we define body force term. Our body force term is this, so that this analytic solution for this is available, which is sine pi x, sine pi y. So this is how we chose body force term. Okay, let's now define the body force F, which is given in terms of the analytic exact solution. And exact solution is this, sine pi x, sine pi y. And this is again given in terms of the spatial coordinate. So we call this spatial coordinate function to get the symbolic representation of the coordinates. And okay, we have defined our body force term. And as before, we define a test function and trial function on function space V. And we define bilinear form, which is just grad u dot grad b, and linear form. This is just f times b. Now we are left to define our dirichlet boundary condition. So this is a new thing. So let's take a look at the notebook. The constructor of dirichlet BC takes the function space on which the solution lives and the boundary value. In our case, we have homogeneous dirichlet boundary condition. So this is just 0. And the subdomain, this is the labels of the boundaries on which we define, on which we have a dirichlet boundary condition. And please forget about the last argument. This has been expanded, so please don't use it. And so to apply dirichlet boundary condition, we have to specify the boundaries, subdomain IDs of the boundaries on which we want to apply dirichlet boundary condition. So we have already seen this, but let's double check how we define how the boundary labels are defined for unit square mesh. So scrolling down, here's the definition for the boundary labels. The left boundary is labeled as 1. Right boundary is labeled as 2, and so on. And we have homogeneous illicit condition all over the boundary. So our boundary ID is a tuple of 1, 2, 3, 4. So we are ready to define the illicit BC object. B is the function space on which our solution is defined. We have homogeneous illicit boundary condition on boundaries labeled 1, 2, 3, 4. Now we solve our Poisson's problem with boundary condition. So we are solving for A equals L, and we define UH a function on the function space B, in which we store the computed solution, and we prescribe our boundary condition. So this is new thing, and this internally modifies the function space so that this boundary condition is applied strongly. And again, we have some solver parameters, which is directly passed to PET-C. We again use conjugate gradient. And let's solve this. Plotting. And the solution looks good. So yeah, now I think please go ahead and complete exercise. This is pretty much the same problem, but we have slightly different boundary conditions. And there are several helpful hints, so please look at these. And maybe we can have, I don't know, 5 minutes to complete this exercise. So yeah, please go ahead.
So Carlos has asked, is there a straight way to find the source term f from an external numpy array, which could be potentially defined over a rectangular grid? So the thing, Carlos, is that you as the user don't directly know what the grid numbering is. And in particular, if you think about what happens in parallel, and we will get later on to how you run Firedrake in parallel, but none of this code changes in parallel. But obviously the mesh is going to be partitioned under the hood, so each processor won't even know which bit of the mesh it's got. So attempting to get inside the data structures to specify data yourself doesn't work very well. But what does work very well is if you provide a function which can be evaluated in space, which provides values, for example, because you're interpolating them from some external data source, then there is a recipe in the manual that gives you a very straightforward way of doing this. Essentially, it's relatively straightforward, at least for the more straightforward function spaces, to get a list of the coordinates of all the degrees of freedom and to set the corresponding coefficient values for those degrees of freedom by interpolating. And that's essentially the recipe for getting external data in. David Haynes says, how could I specify a piecewise linear function on, say, gamma 1? There is a UFL operator called conditional, which does that for you and acts like a ternary operator, basically. The one thing you need to be aware of in using conditional is that Python binary operators, binary comparators are not overridable in the way you would like. And so it's not really possible to get them to produce symbolic objects back. And so you have to use special UFL operators for that. I will just check our documentation and find you an example, or someone else can beat me to it.
I think DG advection has lots of conditionals in there for the initial condition.
That's probably right, yeah. Time dependent DG advection. It does, although that's possibly already overkill, but okay, I'll post that one. So
it's a very nice example for showing what is possible with the UFL condition.
that's right. It's not the easiest case you could think of, but it is. This is in here. Is that going to work? How's that? Yeah, that's basically right. So if you look at say the definition of slot sill, which for those of you who are familiar with the Randy Levesque classical advection case, is a cylinder with a chunk cut out of it, which is known to be a hard case for advection, which is why people use it. Then this is checking that it's a conditional for the coordinates x, y being within a certain radius of the center of the cylinder and not being in the slot. And you can see here how that works. This is a slightly easier example, which I can steal from Andreas Klockner's course at your IUC, because it's very nicely online.
I think we can now look at the solution. We got 5 minutes to the break. Let's start. So we again have the Poisson's problem on the unit square. So let me just let's again use the same function space. And define our trial function on V and our test function. And let's define our big form by linear form. It's just dot times dx, right hand side, linear form is constant times times dx. And here we cannot just say zero, literal zero here. Literal zero is reserved for nonlinear problem where left-hand side is a residual. In this case, left-hand side is by linear form, so right-hand side has to be linear form. So we have to do this multiplied by test function. Okay. So if we had a non-homogeneous Neumann boundary condition, we would have to include some appropriate boundary integral term here. But in this case, we have Neumann boundary condition, but it is just homogeneous. So we don't have any additional term. And we now have two differential boundary conditions. The first one is again the solution lives in V, and the first one, the value is 1. This is on gamma 1. Gamma 1 is y equals 0, which is labeled as 3. You can always check the documentation. And the second boundary condition is DC. Again on V, the value is 2, which is on gamma 2. It is the top boundary, labeled as 4. Now we are solving the problem. So this is where we store the solution and we solve A equals A, store solution in UH, and BC equals, as one of the hints suggested, we can use a list of boundary conditions. So BCs can be a list of BC objects. So BC1, BC2. And we can optionally put some server parameter. But we can also use just default one. And solve this. Oh, nice. If we want to plot the solution, let me just copy and paste. Okay, it looks like 1 plus y. And let's check this numerically. So y, we need y. So we do this. U exact equals 1 plus y. And what we can use is error norm function. And if we want, we can check the documentation like this. Error norm function works like this. UH, and it computes the L2 error norm by default. It looks good. So this is the end of this, I think, tutorial and the first session. And I think we have 20 minutes break here. So yeah, please come back in 20 minutes.
Yeah, that's right. We will mostly be hung around here. So if people want to ask questions or if anyone's having technical difficulties, you can do that in 20 minutes. But we will otherwise, you can go get a coffee, read your email or whatever, and we will start the next session in at 12:30. Zoom tutorials are very bad for this part, because this part normally we just sort of wander around the room and chat to people, and it's all quiet and everybody's cameras off, views on.
Yeah, I do miss that physical aspect of the in-person tutorials.
There's a thing called Gather Town, which is like a 1980s video game where you wander around. I've only used it once. It seemed to be surprisingly useful. I don't know how well it would work with technical training, but for sort of virtual, I just saw it used for a virtual poster session. It worked quite well because you could wander up to a poster and immediately speak to the person there and not have to talk to the whole room. But it's no excuse. It's no substitute for just wandering around and chatting to people.
So anyone who is free on the 15th to the 17th of September, we will be holding the Firedrake meeting, which will have a Gather Town poster session, and in fact Gather Town socials between all the sessions. Thank you, David, for that. Well, I promise you we did not set up David to say that. Yeah.
Yeah, we should possibly pop a link into the
Amin says, how do you define the third BC in the exercise? Which third BC?
Maybe in general,
Or
I think.
or do you mean the Neumann condition?
Oh,
The Neumann, okay, so the Neumann condition in this case is what is referred to as the do nothing condition. So the Neumann condition on the sides is grad u dot n equals 0, and that corresponds to simply not writing down that integral. So we just so you literally do nothing. So that's the same as what happened in the first exercise. So in the first exercise where we did modified Helmholtz, and we had a Dirichlet, a homogeneous Dirichlet condition everywhere. So it was grad u dot n equals 0 everywhere, and that just corresponded to crossing the boundary integral off and not coding it.
So Jack suggested I test my screen sharing during the break, so I'll see if I can get it working. So get rid of those. And I'll turn my video off as well. So hopefully you can hear me, and hopefully you can see it scrolling at the minute.
Yeah, it seems to be okay.
Yep, looks good.
Yeah, all fine.
Good. Yeah, I'm running it locally now, so hopefully that'll be better.
Okay, I make it half past, so we should probably recommence. Joe, you're on next, yeah?
Sounds good. Yeah, we'll get started. I'm now doing the notebook locally, so hopefully there won't be any connection issues, but I'll turn off my video as well, just in case. Okay, so hopefully you can see the next notebook. So, sorry, that's the top of the next notebook. So it's the third one on the list on linear elasticity. So again, we're solving a steady state linear PDE. The difference is that where the PDEs that we've considered so far are all scalar valued, we're now considering a vector value problem. So we'll consider the equations of linear elasticity in the isotropic case. So the first equation that we see here is the equation which governs small deformations in linear elasticity. So we've got a negative divergence on the left-hand side, and then a forcing term on the right-hand side, where we're taking the divergence.
Joe, we've lost you again. Right. We clearly, Joe just doesn't have a good enough network connection for this for some reason.
Is it worth him trying to dial in using the telephone interface?
I think for the moment, someone else will just have to present it. Shall I do the linear elasticity?
Yeah, if you're happy to, David.
I haven't needed to go back and do any bailing out of Azure stuff. So let's assume that I am free to do this.
So I can attempt to narrate again. Hopefully that works, if you don't mind.
Yeah, okay, we can do that. I will share and then we will see what happens. And if you drop out, then I will just take over. That is not this, that is me building the containers. Here we go. Elasticity. Is that big enough for everyone?
Looks good to me.
Okay, go ahead.
Thanks. Yeah, apologies again. I believe I got to the point where I was saying that we have divergence of the stress tensor here, which is defined in terms of the symmetric strain rate tensor epsilon, which is an average of this gradient of U and its transpose, where U is the unknown vector displacement field, which we're aiming to solve for. And then there's two Lamech parameters, mu and lambda. So as before, we've got a variational formulation where we start by multiplying by a test function from a suitable test space and then integrating over the domain. The difference here is that where before we had a scalar test space, now it is vector. So we have a dot product as opposed to just multiplication. So the solution U lives in the same space and is also vector, as I mentioned. And since sigma is a function of the derivatives, we integrate it by parts, which results in the following equation. So we've got this first term over the interior of the domain, and then we've got a boundary term which involves the normal component of sigma. And the right-hand side remains unchanged. It's not multiplied, integrated to our parts. So we also need to specify the boundary conditions. So we've got the condition on the traction. So we've got a Dirichlet condition, and then we also have a Neumann condition, which is imposed weakly. So to consider the concrete setting, we're now taking a displacement of a beam under its own weight, where it's clamped at one end. And we've got a rectangular domain here with a length and a width as specified. There's a Dirichlet condition, which is the clamp. So there's no displacement on that component of the boundary, which is given by the plane x equals 0. So everywhere else is a traction-free conditions. And effectively here, we've just got the only force which is acting on this beam is gravity. So we're going to see that appear in the forcing term. So as with all the other notebooks that we've considered so far, we start by importing Firedrake as well as some plotting functionality. The difference from what we've seen so far is that the mesh now, it's a different utility mesh provided by Firedrake, but instead of being unit square, it's rectangle. We've got different numbers of cells in each direction, and it's no longer square. So we need to just define the function space. It's almost exactly the same as before, but instead of having just the standard function space, which is assumed to be scalar, we have a vector function space now. And by default, this is going to have the same number of degrees of freedom as the dimension of the space. So we've got a 2D problem. So there's just going to be the x component and the y component of the displacement. We need to implement the clamp, i.e. the Dirichlet condition on the plane x equals 0. So if you go back to the documentation on the unit square mesh, then you would find that this is the plane number 1. And where before we just put in the number 0, that's a special case for the scalar case. In the vector case, we need to mention that it's a vector constant. And so in order to do that, we wrap it in the UFL constant, where we've got this array 0 in the x direction, 0 in the y direction. So now we define the parameters which are going to make up the weak form. So there's a parameter rho, which goes into the load vector. So this load vector is going to be 0 in the x direction, and in the y direction we have the force of gravity. So there's a material density rho, and then there's also gravity, which we've just taken to be 1 for this particular test case. So you have this UFL function here as vector, and then inside the brackets there's 0 in the x direction, and then negative density times gravity. We've got a couple of parameters I mentioned before, which are just taken to be 1 and 0.25. Note that you can't define something lambda, or it's not a good idea to define something lambda in Python, because that means something else. So we've put an underscore just after it. You don't need to worry too much about that. And then because we've got a vector problem, there's an identity matrix which appears in the formulation, and we need to define that in terms of the geometric dimension. So as I mentioned before, there's a couple of formulae that we're using for the stress and the strain. So we can implement those in Firedrake just as Python functions, which read in the displacement and then give you the representation of the stress and strain in UFL. So you'll notice here the appearance of terms like grad and div and the transpose, all of which are defined in the UFL. And then finally, we're ready to solve the problem. So we've defined the function space, so we can construct these trial and test functions again, noting that these are vector as opposed to scalar expressions. We can form the left-hand side as the inner product of the sigma of u and epsilon of v. So if you go back and take a look at the weak formulation, then you can convince yourself that that can be expressed in this form for the test functions. That can be part of the exercise, I guess. Thank you, David. And we're going to again create this UH, which is going to hold the solution data, pass in the boundary conditions which have been defined above. So that's the Dirichlet conditions for the clamp. Yep, just there. And then finally, as one of the solver parameters, we're passing in this KSP monitor. So again, KSP refers to the linear solver in PETSI. And when we use this here, it's going to spit out the progress of the linear solver as it runs. So if we can run that cell there, we'll see there should be a few iterations of the linear solver. In this case, it's just 2. So there's the initial residual, and then there's residual after the first iteration. We notice that it's converged in one iteration. That's because, as was pointed out earlier, our default preconditioner is LU. So yeah. And then we can visualize the solution in a very similar way as to what we've done before. But since we're considering a deformation of a plate, it'd be quite nice to see what the displaced space looks like in terms of a mesh transformation, because here we have displacement in XY coordinates, which we can interpret as the coordinates of the mesh plus UH. So this is one of the nice things about Firedrake, representing the coordinates of the mesh as in UFL. And then if we call this here where it's been interpolated into the same space, then we should, well, we're not plotting it just yet, but that's created a new mesh. You see there's this constructor capital M mesh, which you could also use that to load from data as well, which you might see in other notebooks that aren't in this workshop. And then finally, using a very similar APIs to what we've seen previously, we can plot this mesh using, yeah, it's quite similar to the matplotlib functionality. And you can see that this plate has been clamped on the left-hand side where x equals 0, and then it's deformed under gravity. Great. So that's a very brief introduction into how we can solve vector value problems in Firedrake. So just for about 5-10 minutes, we've got an exercise which is to go back and change the density. So instead of having a constant material density, we're going to change it so that it depends on the mesh coordinates, so that further away from the clamp, we have a denser material. And there's a couple of hints there as well if you get stuck. And please do make use of the breakout room functionality or the chat if you need.
Shall I just do this one because it's quite a short exercise? So probably some people have already got it out, and that'll enable us to go on to the more fun one. So we basically tell you how to do this, right? So what we're doing is we're changing the definition of row, and to do that, we'll do what we've done many times before and use the spatial coordinates that we can get from the mesh. And so if we go back up to where this is defined, take these in, and then we can just change the definition of row. Then run this, and then what I need to do is go back and run all the other cells that might depend on this. And you can already see that something's happened because the problem's a little bit less well conditioned than it was before, and LU had produced a slightly less good solution. And if we look at the solution, you get something that looks like this. Now that is clearly massively unphysical, but that's because what we've done is we've taken the we've increased the gravitational force to the point at which this problem is really in no way linear. And so this is the difference between maths and physics. This is a perfectly well-defined maths problem, but please don't expect it to look like a beam. So that's what happens when you do this one. Joe, do you want to take over?
Sure. Yeah, thank you for that. Yeah, so as it says in the next section, solving bigger problems, which is definitely a theme we're going to come back to later when we move on to solving problems on Archer. Up to now, we've only solved very small problems, and we haven't had to worry about tuning the solver parameters, and we've just used the default in a lot of cases. But as we increase the problem size, this direct solver approach isn't always going to be good enough. So Firedrake uses PDEs to provide solvers, as we've discussed, and the PDE solver parameters control them. So we'll go a little bit more into the detail of how that works. The next cell here is just the same as all the code we've seen before. The difference is it's just wrapped it in a function for ease, so that we don't have to go back and click through all the cells like David just had to. So if you could just click the next cell, that would be great. Thanks. Yeah, that one. Thank you. So it's been solved. Oh, sorry. Yeah. So we're solving the problem with the Krylov method, and we limit ourselves to just 100 iterations. And as before, we've got a symmetric positive definite problem, so we can solve it with CG. However, if we don't provide a preconditioner in this particular case, we get a diverse linear solve in those first 100 iterations. So we haven't got good enough solver parameters. We need to try and do something different. Fortunately for this elasticity problem, there's lots of good conditioners, preconditioners which exist. The one that we're going to consider here is smoothed aggregation multigrid. And the implementation of that in PDE is called GAMG, that's geometric algebraic multigrid. So you can see here that the list of solver parameters has got slightly longer. We've still got CG as the linear solver, and then the number of iterations for the linear solver is 100. But now we're passing in this this preconditioner gamg. So PC type stands for preconditioner type. In order to do that, we specify that the matrix type in PETC is AIJ, which is effectively compressed sparse row, I believe. And then finally, we pass this other parameter to the linear solver, the converged reason. So that's just so that it tells us why it converged at the end or why it diverged. And where before we were solving on a relatively small mesh, we're now using 200 elements in each direction. So it's getting slightly larger. So if we could press this solve here. Then we see that now instead of, so when we use the default earlier with a small problem, it converged in one iteration. When we tried no preconditioning and CG for this size of problem, it failed to converge in 100 iterations. However, now once it's preconditioned, it does manage to converge, although it does still take 85 iterations. So it's still not ideal. And it turns out that for smoothed aggregation multigrid to work, we need to provide the preconditioner with access to the near null space of the operator. So this means that we need to provide more parameters to the solve in Firedrake here. So we need to construct this orthonormal basis here, which represents the near null space. So you see here there's B0, B1, and B2, all of which live in the same function space as the solution which we're seeking. The first of the near null space vectors is just the canonical unit vector for X. We also have the canonical unit vector for Y. And then finally, we construct the near null space by taking this minus Y X and interpolating it over the domain. So you notice here that these are going to be functions defined in the finite element space. And we've interpolated some expressions, which two of them are constant, the third one is not constant.
So what's going on here is that if you imagine that we weren't clamping the bar at the end, then the problem would only be defined up to rigid body motions, right? I could move the bar around and rotate it in space and still have solutions. And that would be a true null space. And it turns out that when we clamp the end, what we have is a problem which is close to singular in the with respect to that same null space. And that's what we're taking out here. So this is displacement in the vertical, displacement in the horizontal, displacement in the vertical, and rotation.
Yeah, thanks very much for expanding on that. And then finally, once we've created this vector space basis, we orthonormalize it in the next step. And then, as we've seen before, we're just creating a function to store the data, passing in the boundary conditions, the solver parameters, which are going to be passed into the function that's currently being defined, and then finally the near null space. So in the next step, it's the same size mesh, we've got the same linear solver, the same preconditioner, and the same matrix type. The only difference is that we've made it aware of the near null space. So if we could tap through on that one, please. Then if you remember, the previous one took 85 linear solver iterations, whereas now we've got down to 28, which is clearly an improvement. So the final exercise for this notebook, which is slightly longer than the first one, is to study what happens to the number of iterations when you change the mesh resolution. So because we've put in this solver parameter KSP converged reason, it's going to tell us the number of iterations. So it should be fairly straightforward to deduce what the difference is when we try different sizes of meshes. So we'll just leave a few minutes for that. Our original schedule says that we would like to finish this in 5 minutes. So I think we should be on track for that.
I see David has his hand up.
Yeah, so apologies, I'm not really a finite element person, but when you did that, is it get mesh? You get the physical coordinates of the mesh. I can't remember what the function was called.
Spatial coordinate.
Are they the nodes, or are they the centroid of the elements, or what?
They're none of the above. So X and Y are symbols representing those coordinates. So they're just, I mean, they're really just X and Y, right? And then what happens is that those symbols can be used in expressions, and those expressions will eventually be evaluated at some point in space. And then when they're evaluated, they'll take those values. So for example, when they turn up in an integrand, that integral will eventually be evaluated using a quadrature rule. And that quadrature rule says evaluate the integrand at each of the quadrature points and take the weighted sum. And so when the integrand is evaluated at each quadrature point, X and Y will at that point take the physical location of the quadrature point. So you take the quadrature point in local coordinates and push it forward through the change of coordinates to give you the
okay, so it's more of a formal statement than you're not actually saying, well, give me the, okay. What it means depends on the context of how it's used, is what you're saying.
That's right. So just as indeed so it's more blatant with the physical coordinates. But if you think about when we write down a function in a function space or a test function or a trial function, we actually have the same problem. Just like X and Y, those are functions of space, and we didn't tell you where to evaluate them. And that's because that makes sense in the context in which they're used.
I'm surprised that it uses, I mean, that wasn't incomplete LMU, that was complete, that was full LMU as a preconditioner, which is sort of, well, it's solving the whole thing before you start, isn't it? I'm surprised it even has that as a potential default.
So the reason why we set that as a default is that if you are, the typical beginning Firedrake user solves small problems where what they're interested in is working out the properties of the discretization. And then they move on to solving problems at scale where a different solver would be more appropriate.
Okay.
The other thing to be aware of, so one of the dirty secrets of solvers is that if you are in 2D, it's actually really hard to beat a direct solver. So in 2D, the bandwidth is sufficiently constrained that a good direct solver, and we use by default mumps, which is a good solver that works in parallel, the default solver is actually the right thing to do for most 2D problems. And for 3D problems where the bandwidth is larger and also the problem size grows so much more quickly, the right thing to do is essentially completely dependent on which PDE you're solving. And so for the cases for which there is a sensible default, the sensible default is basically to do a direct solve. And
it's, so mumps is all sparse, isn't it? Mumps is already very,
that's right.
Very
all of this is always sparse. The one exception of what happens when we apply scalar constraints, so Lagrange multipliers, it's the only time you'll get something dense in a matrix. But
it's just sparse direct solvers are quite tough. Well, the bookkeeping can get a bit hairy.
Well, one of the nice things about PETSI is that it gives you an interface to other people who solved that problem for you. Yeah. So, but you're right. And like mumps is pretty geriatric and sometimes has some pretty horrible failure modes because its memory management is bad. And the fact that mumps has not been superseded in a very long time is indicative of what you just said, that this is a difficult problem. Okay, shall I do this?
Yes, sure, you can do. I was going to say I've run it and I can just post the output in the chat if.
Yeah, or I can just copy and paste them into here, right? So yeah. If I so what do I want to do? I want to run this at 10 by 10. And it converges in 13 iterations. And if I run it at converges in 21 iterations. So remember the number of degrees of freedom is scaling like resolution squared. So that's actually pretty robust. It's not completely robust, So by robust, we mean in an ideal world, the number of iterations would not go up as we increase the resolution, but it's not bad. It would get better if we used a geometric multigrid method, but that would be getting ahead of myself. We'll do that later. So that goes to 23, and then 200 goes to 28. So as we can see, so when we go from 10 to 200, you're increasing the number of degrees of freedom by a factor of something like 400, but your number of iterations is doubling. So that's reasonably robust, and it gives you the hint that for this sort of problem, algebraic multigrid GAMG is quite a good idea. I should stop this share. Who's doing the next? Why did we use GAMG as a PC? Someone's just asked me. The reason we use GAMG as a preconditioner is that if you are solving an elliptic problem, then multigrid solvers are optimal because the problem is globally coupled, and the multigrid solver turns the transmission of information over an entire mesh into the transmission of information up and down a tree representing the mesh, and that's vastly more efficient. It's usually the case that for a globally coupled problem, the optimal solver is something that turns your problem into a tree. So Koki is now on to give us nonlinear and time dependent.
Yep. So now we take a look at Berger's equation. There are two new things. This is time dependent and nonlinear. And this is Berger's equation, and this is the time derivative, and this is the advective term and diffusion term. And so that we don't have to worry about boundary conditions for this problem, we use a periodic interval mesh. So there's no boundary, that's virtually no boundary. So as before, we want to find our weak form. U is our solution, and U lives in some function space V, and our test function for this problem lives also in V, and we apply our test function to this strong form of the PDE, nonlinear PDE, and get our weak form like this. So this is the straightforward, and to get this term, we apply divergence theorem to this to bring the second order spatial derivative to the first order spatial derivatives. And we do not get boundary terms here because we have no boundary. So this is our weak form. And for this problem, we've yet to discretize in time. And for simplicity, we first use backward Euler method. So this is the approximation to our time derivative of u, un plus 1 minus un divided by the time step size. And everywhere else, we replace u with un plus 1 because we use backward Euler method. So to solve this problem, we have to define test function and un, the current solution, which we assume that we know, and un plus 1, the solution at next time step we are solving for. And here's a bit more about this problem. We start from initial solution, initial condition u0. So we have to specify initial condition sin 2 by x. And the idea is we substitute u0 here and solve for u1. Once we get u1, we substitute u1 for un and solve for u2 in the time loop. And this is our initial condition, and this is our viscosity. This is just 0.01. And let's do some more setting. As mentioned, we use periodic interval mesh, which has 100 elements, and the length of the interval is 2. And let's define our initial condition, which is signed to by x. We have to get x. So we again get the symbolic representation of our coordinate using special coordinate function. Even though this is a 1D problem, we still have to index it. And this is how we get a symbolic representation of x, which we use to define our initial condition. And we also define viscosity U. And we now define our function space. We use a Lagrange finite element of degree 2 on this periodic interval mesh. This is a function space. And what we need are three things. The test function on the function space V. And as mentioned, we need to define functions representing the current solution and the solution at the next time step that we solve the equation for. Okay, so first we want to initialize our UN, the current solution, to the initial condition. So we can use this interpolate method in Firedrake to do that. We have already defined the UN. So we can just say UN.interpolate whatever the UFL expression here. And we also define the time step size. Okay, now we define our F, the left-hand side, the residual of our problem. So this is basically the this weak form we just found, but we just have to translate it into to a UFL expression. So we have this is the approximation to the time derivative, and we have advection term and viscosity term here. And this these are all UN plus 1 because we are using backward Euler method. And this UN plus 1 dot dx0 is basically the x derivative of UN plus 1. Just for the plotting purpose, we decode our computed solution at each time step. And okay, finally, this is our time loop. So in each time step, we call solve function. And we say, okay, we are solving for f equals 0 for UN plus 1, given UN. And once we solve the problem, we assign the solution we just computed to UN so that we can use it in the next time loop, in the next time step to compute the solution a step further. And we keep doing this in our time loop. So one thing to note is the right-hand side here is literal 0 because now the left-hand side f is our residual, and this is the nonlinear problem. This is not a bilinear form anymore. And one thing, one nice thing about using Firedrake is thanks to UFL, we don't have to compute Jacobian, the variational derivative of the residual with respect to the solution by hand. We don't have to do that by hand. Firedrake does it inside using UFL package. So that is a really nice thing. And we append the results as mentioned, and we implement time step. Excuse me. And let's plot the solution. And this is a bit boring because this is just the initial condition. And so let's take the 50s solution. And looks a bit more interesting. And we can also create animation here. We can do many things using matplotlib, and I'm not going into the details here because we want to focus on some numerical things. Taking some time. And let's look at this solution. It looks right. Interesting. So going back to our time loop, and so this solve is a high-level convenient function, which computes a Jacobian inside, and it also creates some relatively heavy solver object. So if we keep calling solve function inside time loop, we repeatedly compute the Jacobian and construct and destruct the solver object. We do this. We end up doing that at every time step, which we actually don't want to do. So what we want to do is expose some lower level things here, like this. So we first define a nonlinear variational problem object. We are solving for f equal to 0. We are solving f equal to 0 for un plus 1, and define a problem object. As soon as we do this, this internally, this class takes the variational derivative of f with respect to un plus 1. So Jacobian is computed. And this is done only once. And we then define a nonlinear variational solver, and using this problem we just defined. And optionally, we can put some solver options here. But we just don't do this here. So we create the solver object. And this only happens once again. And the idea is, in the time loop, we keep calling solve method of the solver object. And this avoids decomputation of the Jacobian and construction and destruction of the solver object at every time step. So this is supposed to be much faster. Yes. So exercise 1 asks us how much performance gain, performance improvement we can observe by exposing these slightly lower level objects and using solve method. And exercise 2 tells us to use Crank-Nicolson time integration scheme instead of backward Euler method. So yeah, please go ahead and work on this.
No, the Jacobian will get, nonlinear variational solver will recompute the Jacobian. The distinction is it doesn't have to rederive it. So there's two stages, right? There's the symbolically deriving the expression for the Jacobian, which is done by automatically differentiating the residual, and subsequently then doing the code generation and compilation that gets you the code that would assemble the Jacobian. That's one step, and that will happen once in nonlinear variational solver. But then there is evaluating the Jacobian and producing a Jacobian matrix for each point, and that will occur for every Newton step, unless you tell PETSI otherwise. So you can instruct PETSI not to change, not to recompute the Jacobian, but that would be a solver option. It's not changed by whether or not you use solve. You can also deliberately lie about what the Jacobian is. So you can do a pseudo Newtonian method by explicitly passing a symbolic Jacobian into the nonlinear variational problem or solver, and that would be useful in the circumstances where pseudo-Newton methods or quasi-Newton methods are appropriate. So Koki, do you want to show the answers before we actually formally take a break?
Yeah, sure. Okay, so I copy and pasted some of those cells we walked through, and the only thing I changed was now that the periodic interval mesh has a 1,000 element. So let's execute this cell. Okay, as instructed, we use timing to measure the time. So here we use the naive solve function in the time loop. So we do symbolic Jacobian computation and solve object construction, destruction at every time step. And it takes some time. And for the second half, we do this in a smarter way. We export some of these lower level objects and call .solve method.
Sorry, Koki, it looks like you might be missing the timer in the second one.
Okay, sorry. So it's going to be much faster. So for the second one, as instructed, we define G, and using G, we can define our residual like this. So the only difference is here, we use G to define our weak form. And we again do the same and solve this problem like this. So the really nice thing about using Firedrake, which uses UFL, is that every time we don't have to compute Jacobian. Every time we change, we switch the time integrator. So you might have noticed that we just have to change this definition of residual, and Firedrake automatically compute Jacobian using UFL, which is really nice. So it's taking some time, but that's basically the end of this.
I think it's your previous one that's taking time.
Yeah, so I forgot that I was running locally.
Yeah, Koki's laptop is run by a small gerbil on a wheel. So one relatively new thing that's out here. So running time on Python code is, of course, really convenient if you are just mucking around interactively. It provides limited information and is not such an easy thing to do if you wanted to run a big problem in parallel. And there's some very recent developments in Firedrake, which are documented in the manual at the location I'm just posting, in which Connor Ward, who's one of the PhD students working on Firedrake, has set up automated generation of flame graphs from Firedrake runs. So you can run with the options specified there, and at the end you can get a nice SVG that tells you in a cascading way how much time was spent in every part of Firedrake. And that's an immensely powerful guide to optimization. And importantly, that will work in parallel. So you run in parallel and it will give you a flame graph based on the maximum time taken in each stage by everyone. Dave's just put his hand up.
So to Firedrake, but PETSI is a single thing as far as Firedrake is. It'll say this much time spent in PETSI. Well, I guess you can't look lower than that because it's. No,
it will tell you how much time is taken at each level of PETSI. So it's actually, PETSI has an internal events mechanism, which we leverage and extend. So actually it's the other way around. We're taking what PETSI does and bringing it up to the top. And then actually all this magic flame graph stuff was implemented by extending PETSI and having PETSI accept our patches. It's actually, which happens quite often. So we sit kind of on top of, or sometimes in the middle of, quite a deep stack. And sometimes the changes we make are in other people's code.
Okay, thanks.
So I guess it's 20 past now. So this is the second break. So we're going to take this break, and after this break, we'll come back and introduce a mixed problem. And the reason we're introducing a mixed problem is that we're then going to solve a mixed problem on Archer. No, we're not solving a mixed problem on Archer. Okay, we're going to do a mixed problem because that's the next level of complexity, and then we're going to solve a problem on Archer.
Yeah, I was going to ask if anyone hasn't yet managed to connect to ARCHER2, this break will be an opportune time to just make sure you can connect to ARCHER2, because we'll be using that at 4 o'clock. And yeah, we'll be around if there are any questions or difficulties with that.
Okay, so there's a conversation going on in the chat that I will shift to orals because it's easier. So the world of a PDE solve is you have a nonlinear solve on the outside, which is called the snares. And that contains a KSP, which is a Krylov-based method, which has a preconditioner. Now, all of these things nest, so any of these things could also contain another one, but that's the basic setup. And the way that you do less than all of that stack is by switching bits of the stack off. And so if you do not want to use a nonlinear solver, for example, because your problem is linear, then you say SNES type KSP only, which says only do the linear solve. And if you, so now in PDE's world, a linear solver is always a Krylov method, and anything that isn't a Krylov method, such as a direct solver, is a preconditioner. So if you only want to use a preconditioner, for example, because you want to use a direct solver, you say KSP type pre only, and you set the preconditioner type. Conversely, if you want to use an unpreconditioned Krylov method, you set the KSP type to whatever it was you wanted to use, and the PC type to none.
Well, yeah, let me explain why I asked this question. Yeah, recently I was working on some fluid structure interaction problem, and for that we had to enforce some degree of freedom, internal degree of freedom to be 0 using the differential boundary conditions. And well, when we try to use the linear solver, then definitely it used the it used non-linear solver, but the pre-KSP only option. It seems that solves the adjoint problem as default at least once.
No,
You don't think so?
So Firedrake itself does not automatically solve adjoint problems.
Okay, yeah, I'll look at more details. But
so in order to have, so there is an automatic adjoint facility, but that is provided by PyAdjoint, where you have to, if you have to import PyAdjoint, you have to tell it to solve an adjoint problem. And that's built in now, so you don't have to separately install PyAdjoint, but you do have to ask for Firedrake adjoint and tell it to compute an adjoint solution. It won't merely solving a linear or nonlinear variational problem will not cause an adjoint solve.
Okay, well, yeah, then I'll look at the code in more detail. Yeah, thank you.
Yeah.
There's a question in the chat. Someone says, will this recording be made available after the course?
Yes, EPCC have agreed to host a recording of these of this tutorial. So it'll be linked to from the site you signed up on.
I notice as we get to the good bit where, or at least the bit I presume people here are interested in, where a few people down on where we started. Oh, well, they're lost.
Hopefully we'll have some come back. I've been some people have been dropping off and I've been letting them back in.
does Imperial put quite, if we only recently got Zoom via the university, and they're quite conservative, so I think you have to have a waiting room for externals or something. I couldn't set up quite how I wanted. So I think they're a bit conservative about Zoom bombing and things.
We can set up almost anything we like, but because this Zoom address is approximately public, it's set up with a waiting room to avoid Zoom bombing. But no, other meetings we run that are less publicly advertised, we don't run waiting rooms. But it is infuriating when central ICT decide that they know better. My favorite last year was in the last summer when we were frantically trying to get everything ready to go online. Imperial's IET department decided to run a 1-month consultation into whether Imperial should acquire the GitHub Enterprise license that it had already had for 5 years.
So we're scheduled to start around now. Would it be okay if someone shared and I could narrate over it? Again, apologies for the connection issues. I don't know if you would like to do that.
Yeah, I can do that.
Thanks very much.
Pull up let me find the right thing and then I'll share. Mixed Poisson. Why is something vaguely fishy about Poisson? Share the screen. Here we go.
Thank you. Great, so now we're on to the 5th notebooks. This is the last one we're going to consider on the cloud platform before we dive into considering Archer in the final one. So everything we've done so far is solving a PDE for a single solution variable, so be it scalar or vector. However, in a lot of applications, we actually want to solve for a tuple of variables. So effectively, that means solving a mixed. You solve the finite element problem in a mixed function space. So there's different components for each of the solution components. So we're going to take Poisson, which we've already solved in a standard formulation, but we're going to solve it in a mixed formulation instead, just to show that we can do that, and to explore the different solver parameters that are available for such formulation. So the first 3 lines that you'll see is the same Poisson problem we've already seen. There's a forcing term on the right-hand side. There's a Dirichlet condition, which may or may not be 0. And then there's a Neumann condition, which again may or may not be 0. We can obtain an equivalent form by now introducing a new variable, which is sigma, defined as the gradient of this variable u, the scalar variable u. So sigma is now going to be vector variable, so valued. And then when we have the corresponding formulation, there's now 4 equations. So there's 2 which are on the interior of the domain. So the sigma in terms of u, then the sigma in terms of the well, it's divergence in terms of the right-hand side, and then again we've got the same boundary conditions. But you'll notice that for the second one, it's now sigma. The normal component of sigma is equal to g on the Neumann segment. So using the same approach that we've done so far, we multiply it by test function and we integrate over the domain. But it's worth noting that now, because we have this mixed formulation where there's a sigma component and a u component, which both live in the corresponding spaces, capital sigma and capital V, we're also going to have test functions which come from each of those spaces. And then those will be multiplying each of the 2 equations. So in the first case, we have tau, which is a test function from the vector space. So you see that there's a dot product there, and the same in the second bit. And we've integrated by terms, by parts in that term as well. And then for the second one, v is a test function taken from the scalar test function space v. So we've just got the divergence of sigma multiplied by v equals the forcing term multiplied by v. And you can also note that how this has affected the boundary conditions. So where before we had a strong condition in the primal for the auxiliary variable sigma, how the weak condition in the primal form becomes a strong condition on sigma, and the strong condition on U in the primal form becomes a weak condition on sigma. So it's a little bit confusing when you just read it out, but you can try and convince yourself that that's true as an exercise. So to consider a concrete case, again, we're going to consider the unit square. We're going to have 0 Dirichlet boundary conditions, and then the forcing term is going to be a negative exponential. So it decays exponentially, starting in the center of the domain and spreading outwards. So as you've seen many times already, we're going to start by importing a few modules, including Firedrake, and defining a unit square mesh, which is relatively coarse. So because we've got this mixed space, there's a few technicalities related to how we choose the two spaces so that we have a stable discretization. And I'm not going to go into all the details of the maths here, because at the end of the day, we're mainly concerned with the numerics for this particular workshop. But one suitable choice is to take a Ravier-Thomas space as indicated here. So I should also mention that with the function space, so far we've just been passing in the mesh and then a string which defines the finite element and the degree. That's one way of doing it. An alternative way of doing it is to define this finite element object, which is defined in UFL, and then passing that to the function space constructor. So this allows a little bit more flexibility of some other parameters that we're passing in, such as this one here, which is to do with the degrees of freedom. And so this defines the scalar space. We're using Ravier-Thomas there. And then I think we're going to use DG for the vector space.
The way around.
Sorry, yeah, other way around. Thanks. And okay, so there's a technicality here on how exactly you the notation that you use for the Ravier-Thomas space. And then to get the mixed space, we take the product of the two of them, or I guess the direct sum, and then we can extract the trial functions and the test functions. Note that now instead of using trial function, we're using trial functions, which means that we're going to extract a tuple of the trial and test functions from the mixed space W. And as we've seen before with other right-hand sides, we're going to define F in terms of the spatial coordinates expressions. And when we take the two different parts of the mixed formulation, there's two equations equal to 0, it's equivalent to just write them all together because we're using test functions from different spaces. This is one of the properties of the finite element method. And so for the bilinear form here, we just have the product of the trial and test function from capital sigma space. Then we have the divergence of tau, the test function from that space multiplied by u. And then we also have here the contribution from the other component, which is just the divergence of the trial function sigma multiplied by the test function from the scalar space. So you'll notice that the boundary terms have vanished because we're applying Dirichlet conditions everywhere. And then on the right-hand side, we've just got the forcing term, as we've seen many times before. So in this particular case, we have a symmetric problem, but it's indefinite. So we can't use conjugate gradients because it requires that we have symmetric positive definiteness. So one option is instead to use MinRes, which is a package that accounts for indefinite symmetric problems. And as has been discussed in the chat, you can pass no preconditioners just by saying none, the string none, that is. So this isn't the best way to solve this problem, but it's a good place to start. So it takes a few seconds and it's run, and then we can now plot the two components. And there's a bit of a technicality here because we've solved for function WH, which is from the mixed function space capital W. But what we want is the two separate components. So the sigma h from the capital sigma space, and then also UH. And the way that we do that in Firedrake is with this split command here. There is another version of split, but we don't need to worry about it right now. This version of split is taking the data from this function and then creating two separate functions, or not creating them, sorry, but accessing them. and then we can plot the two of them on the same axes using matplotlib. So the solution of the Poisson equation we're seeking is on the right-hand side there, and you can see it looks like a negative exponential. And then on the left-hand side, we have its gradient, which looks pretty convincing to me. Good. So that's the setup of the problem using a relatively naive approach to solve the linear system. But in most cases, and especially on HPC, we want to consider the preconditioning in more detail, and to achieve parameter-independent convergence, so that the number of iterations of the linear solver should be independent of both mesh refinement and also variability of the coefficients. But we have a relatively simple problem here where all of the parameters and coefficients are constants. And so the thing that we need to worry about the most is refinement. So if we take this coarse problem and we refine the mesh multiple times, are we still going to have a similar number of linear iterations or not? Or is it going to explode as we take a larger mesh? So this code block here is taken all of the code from above and just put it into a solver function for convenience. So n is the resolution of the square mesh in both directions, and then we can pass in different solver parameters to play around and see how the linear solver behaves in relation to that. So if we can click through and go down to the next one, we're again solving with min-res, but instead of using no preconditioning at all, we're using an incomplete Cholesky, Cholesky is a valid choice because we have a symmetric problem. And in order to use incomplete Cholesky, we need to specify that the matrix type is sparse compressed row. There's also some timing functions here, which will they'll time each solve on the different resolutions that we're leaping over. So we're starting with 5 elements in each direction and then going to 10, 25, 50. And what we want to see is as this resolution is increased, how do the number of iterations change? Does the iteration even still converge? And then finally, how long does it take? So if you could click through that one, please, David. And we'll see that the time is increasing, but also the number of iterations is increasing quite rapidly. So it's doubled-ish the resolution as we go up. It's not quite multiplying by 2 every time, and you see that the number of iterations is increasing in a relatively similar way. So this isn't desirable because this is still a really small problem. 50 cells in each direction is still a very coarse problem, and if we want to go to HPC, this just isn't good enough. So we need to think a little bit more about these solver parameters that are being passed in to the linear solver, 5-PETC. So one way to do this is using a sure factorization. So the system that we have, if you think about it, is represented as a block matrix of this form, where the first term is corresponding to the which one is it? To the vector function space, and then the second row is corresponding to the scalar one. So there's non-zero blocks, which are corresponding to the trial function of the vector space multiplied by the test function of the vector space. And then we've got the non-zero contributions from the trial function of the vector space multiplied by the test function from the scalar space. And then the other mixed term is non-zero. And finally, when you have, there's no contributions, which are trial and test functions, both from the scalar space. So that's an explanation of how we have that block structure. And it's well known in the numerical linear algebra literature. You can factorize a matrix of this form using the following line there, where S is defined as the Shor complement. So if you want to convince yourself that that's true, then you could do some block matrix algebra expansion on pen and paper. We're not going to do that for now. We're just going to assume that that's the case. And it's also well known that this factorization has the inverse on the third line that's currently being shown. And when you're doing preconditioning, you want to multiply by the ideal preconditioner is to multiply on the left-hand side of the equation with the matrix curly A here. We're effectively solving curly A times x equals b. So if we multiply by curly A on both sides, that's the perfect preconditioner. But of course, it's not something that we typically want to do for a large problem. So instead, we can multiply by, if we multiply by the third equation that's currently being shown, that's effectively what we're doing. But in order to obtain such a thing, there's multiple different inverses that need to be computed within this block structure. So an alternative way to approximate this preconditioner is just to consider the middle block. And using that as a preconditioner has been shown in the literature to be a pretty good choice. And so that's what we're going to do exactly using the PETSI infrastructure. It's a little bit more involved now. You can see that the list of solver parameters is starting to get longer, and it will continue to get longer as we consider bigger problems. But let's break it down line by line. So we're still using the same linear solver, MinRes. We've still got the same matrix structure, but now we're using something called field split. And what that does is it tells PETSI that we have this block structure, which corresponds to the two different components of the function space. And then we want to separate them out. We want to use a sure factorization, and the way that we want to do it is in this diagonal sense. So all that means is that we're going to approximate with that middle block at the middle matrix, as opposed to using the whole one or some other section of it. And then we treat the two different components of the field split separately. And again, choosing these solver parameters means you have to think a little bit about the properties of the equations being solved. So the first one here, we're considering the vector equation. And just for now, let's just do something relatively simple and use conjugate gradients as the linear solver. Again, as before, we'll use an incomplete Cholesky preconditioner. And then we'll just specify a relative tolerance as well, and do something quite similar for the scalar component, but without the preconditioning. And let's just see if that improves our performance, which was approximately doubling the number of iterations as we approximately doubled the resolution. So the timing is still increasing, of course. However, the number of iterations is 2 every single time. So this is an improvement in the sense of the iterations, but the algorithmic convergence. But unfortunately, it's still quite slow. And of course, you can see this time is exploding. So if we consider a very, very large problem, it's possible that it's going to take a very long time to solve. And it's because S is effectively an elliptic operator, which is being inverted with an unpreconditioned Krylov method. So you saw that in the second component of the field split, we're applying no preconditioner. So yeah, there. So hopefully, if we change that and choose a suitable preconditioner for the Shor block, then that will improve things. So before, there is a little section here on the PETSI options. I don't know if we want to go into that in more detail or not, or if everyone's happy with how it is. Sorry, David, are you skipping through past the exercise or? Okay, I guess we can do this bit. So yeah, as I mentioned, we haven't been preconditioning the Shor block, but for this particular structure, A is such that the inverse of its the diagonal of A is a good approximation to A inverse. So if that's the case, then a sparse approximation to this Shor complement, the Shor complement with the diagonal inverse is a good approximation to the Shor complement. So the way that we do this with the PETSI solver parameters is by passing PC field split Shor precondition self P. That's the magic incantation that you need to use in order to activate this functionality. And again, we're treating the vector equation in the same way. And the scalar equation, we're using CG. We want to see the convergence, the converged reason of that particular component. But then now for the preconditioner, we're using hyper. Everything else is exactly the same. We've just chosen a preconditioner, which we think is going to be pretty good for that second component of the field split. And because we turned on the logging of the linear iteration, we do see a few more things being printed, but the bottom line is that the number of iterations is staying at 2 the whole way down. And where previously the last, I think we didn't even go to 100 last time, if I remember correctly, but the last time the highest time that we saw was about 8 seconds, whereas now we've gone to an even larger problem and we're still only less than 4 seconds. So this is a real improvement. And we could think about tweaking things further. You know, we could reduce the tolerances, play around with other tricks, and in this case, we could completely just remove the linear solvers on the field splits altogether, and just apply the preconditioner. So this isn't necessarily going to converge in one iteration, but it's a much more efficient way of doing things. So we've got the same preconditioners in complete Cholesky and hyper, and we're just multiplying by them in place of a linear solver. So let's see if that improves things further or not. So in the last one, we saw 2 iterations every single time. That's changed. However, as we get up to a higher resolution, it does seem that this is converging to 41 iterations, which is nice. But a really big advantage is that the time has reduced even further. So it's gone from about 3.6 seconds, I think it was, down to 1.3. So this is looking like a nice scalable solver parameter choice. But yes, it's quite an experimental science. It seems easy when you just read a notebook like this, but doing it in practice can be quite tricky. And just trying out different things, seeing what happens, and knowing a little bit about the block structure of the equations will help you out a lot. Sorry, was there a question there? Sorry, I thought someone said something. David's raised hand. What's the question, please?
So you're focusing on the number of iterations, and the amount of time seems to be going up as n squared, which is what you'd expect, which is good. But I mean, is it not possible? I mean, particularly in parallel, that the number of iterations isn't the only measure. That sometimes these preconditioners can take a lot of time, or maybe yep. I don't know. Maybe not with n. Maybe I'm thinking scalability of the number of processes. Maybe I've got the wrong end of the stick.
No, you're right. So some of these things like ICC requires the computation of a factorization, even albeit a incomplete one, and the algebraic multigrid methods require the construction of the coarsening algorithm by inspecting the matrix. So those things seriously cost, and that's one of the trade-offs that's in here. It's quite a complicated science. Similarly, if you run GMG, which is what you would optimally run for big systems, then the cost of doing the smoothing, so the restriction and prolongation can be a problem, or even the cost of constructing those operators can be an issue. So, I mean, going back to this again, the point here is not that, so Firedrake doesn't make the maths or even the algorithmic limitations go away. What it does is means that you can switch between these options in a tiny number of lines of code, which means that the necessary experimentation to arrive on a optimal or at least good algorithm is vastly easier. It's a scientist productivity tool. Jack, do you want to take the main event away?
Yes. Okay. So I'm going to share my screen and we'll go on to the final section. So there's plenty more notebooks in this list that explore lots of the other features of Firedrake, but we're going to concentrate now on the final one, which is a new one for this session, which is number 12, which is their high performance computing demo. So for those who like to click through notebooks, I will warn you ahead of time. Please do not just run these cells on the cloud server. Some of these problems are quite big and may take a long time to run, or may just crash your session, which will log you out. So I'll give you forewarning, but there is a note here. Don't just run them in the notebook. These are designed to be HPC examples. So we're going to start, as we always do, by importing everything from Firedrake. We're also going to do a couple of other things here. We're going to, again, ignore this warning, extract this parallel printing functionality from PETC so that when we run in parallel, we only see one line printed rather than one from each MPI rank. And we're also going to import the Python time module in place of timeit, just as a very crude form of benchmarking. But as has been said before, there are much better facilities within Firedrake and PETC for benchmarking. This is just a measurement. So the first thing that we want to think about in this notebook is how big your problem is. So we're going to define we're going to solve the primal Poisson problem on a large 3D domain. And we're going to specify the size of the problem in terms of the course grid. So this is what this NX variable is, the size of the course grid. NREF, which is the number of multi-grid refinements we'll have. So this doubles the number of cells at each refinement. So one refinement will double the number of cells in each dimension. So 2 refinements is obviously quadrupling in each dimension. And finally, the degree of the finite element. So in this case, it's 2. And there's a little formula given here, which will calculate n, the total number of degrees of freedom in your problem. And that's the number we want to keep in mind throughout. So in the exercise at the bottom, you'll be asked to calculate the number of degrees of freedom you're considering in your problem. Right, so the problem is the primal Poisson problem. So not the mixed form you just saw, Joe just went through, but the primal one. And we're doing this to try and keep things as the maths as simple as possible, so that we're just worrying about the HPC aspects of this. So we've got primal Poisson, we've got this tricky looking right hand side, but this is only so we can define an analytic solution, so we can compare the solution we get at the end and calculate the error. And we're going to impose homogeneous Dirichlet boundary conditions in this case as well. So hopefully you've sort of seen enough Firedrake today to sort of follow along with what's in this third cell. So we're going to create a mesh, as you've seen before. So we're going to make a cubic mesh, NX elements in each direction. And then what we're going to do is we're going to create a mesh hierarchy, which is used for the geometric multi-grid solver that Firedrake interfaces with PETC to provide you with a true geometric multi-grid solver. And then we take the mesh that we actually solve on to be the finest one in this mesh hierarchy. So this is what this indexing of -1 is. We want the last mesh in the hierarchy. That's what we're going to solve on. We construct our function space on that mesh. And just so you can see for this problem, we're going to print out the number of degrees of freedom. So this is accessed by the dimension method of the function space that you create. And then we set up our test function and trial function, define the boundary conditions, and set up the UFL to solve the problem. And right down at the bottom, we've got our bilinear form and our linear functional. And what we can do is we can actually store this in a problem object, so we can keep reusing it. And likewise, we're going to have a solution variable UH, which we're going to keep reusing. And we'll always solve our problem into UH. Now we're going to consider a range of different solvers. The first one we'll consider is LU, which is currently the Firedrake default. If you don't provide any solver options, you will get the LU solver, which has computational cost n cubed. Now this n that's in this computational cost column here is the total number of degrees of freedom that you saw in the formula above. So with the solvers we're going to look at here, LU, conjugate gradient preconditioned with algebraic multigrid, same again, preconditioned with geometric multigrid V cycles, and then conjugate gradient with a full geometric multigrid, and finally an option that reduces memory and communication costs, which is a matrix-free full multigrid implementation with telescoping. And we're going to define this little Python function here to keep track of our solve. So run solve here will take in the problem instance we created above, and whatever PETSI solver parameters we define. So the first set of options we're going to look at is LU. Please don't run this cell on the cloud server. This is the one that takes a really, really long time and might kick you out. But we're looking at this to explore what happens in the default case. And actually, for a small enough problem, you can just run LU, and LU is a perfectly suitable solver, direct solver for small problems. But as your problem size increases, this gets worse and worse. So inside the PETSI solver options, just so it's explicit so you can see what's going on, we're doing a preconditioner only solve, and the preconditioner type is LU, it's the default, and we're going to use mumps as the direct solver here. And by turning on this SNES view here, we get PETSI to spit out a lot of detailed information about how the solver is constructed. What we're going to do for just a moment here is look at the output we get. So I've run this ahead of time, so we don't have to wait. So you can see with Firedrake, all the solver objects are nonlinear solvers, but in this case, it's KSP only. So we're only looking at a linear solver. And then nested within that, the KSP type is pre-only. So it's only applying the preconditioner. And the preconditioner type is LU. So we're definitely using LU. And then mumps spits out lots and lots and lots of information about how it's set up. And for the purposes of today, we can largely ignore what mumps has spat out. But right at the end, it prints out the runtime, which on my computer was well over 2 minutes, and the error, which is sort of our target. So this takes quite a long time, even for this modestly sized problem. What we can actually do is we can look at the computational cost for all the different solvers we've considered, and you can see as you increase the number of degrees of freedom in your problem size, the cost of LU increases far faster than any of the others we saw in that table. So you can see as we start increasing the problem size, LU just isn't going to cut it anymore. You're just going to be waiting far too long. And you can see that in the logarithmic plot, whilst the other solvers are linear in complexity, LU certainly isn't. Mumps is a very powerful solver for small problems, but for very large scale problems, it isn't going to cut it. So the alternative, as we've already seen, is to use an iterative solver. So we're going to do the first thing that makes sense. So we're going to use the CG solver, the conjugate gradient Krylov subspace method, and we're going to precondition that with algebraic multigrid, and this is what the pre-C Gamgee type is. So we look at that, we see again outside it's KSP only, but the KSP object now is conjugate gradient, and the preconditioner type is Gamgee. And there's also a bit of a breakdown of what Gamgee is doing there. And now you see that at the bottom there, our runtime is significantly improved. So on my local machine here, that took about 30 seconds. And again, you can see the error is about the same as when we did the LU solve. So we're solving to within the same tolerance, but we have significantly improved the runtime. But because we've created this mesh hierarchy, we could also use the same conjugate gradient Krylov subspace solver, but we can replace it with geometric multigrid, and this has the preconditioner type MG. And so here we see KSP type is CG, and the PC object is MG, which is geometric multigrid. And you can see a bit of breakdown of what happens at the different levels. And on the core space, it's performing a direct solve with the LU. Right. And at the bottom, you can see that's roughly comparable in terms of runtime. So this is, because it's all running within a notebook, is all on a single core, single MPI rank. And it's roughly the same amount of time to do algebraic or geometric multigrid. But this is geometric multigrid with V cycles. So one thing we can look at here, so this is performed separately outside the notebook, is a weak scaling study, and there's a bit of detail above about what a weak scaling study is. But you can see that LU is completely out of the question for this. As we increase our problem size, even if we throw more processors at it, the runtime is increasing and increasing. Geometric multigrid with a V cycle is also out. Algebraic CG with the algebraic multi-grid weak scale is a bit better, but it's still more expensive than the full multigrid solvers. So that's what we're going to look at next. And now our PETSI solver options start to expand, as we've seen in previous notebooks. So now we're going to use the full multigrid as our preconditioner. So we've got PC type is MG again, but now we specify the MG type is full, and this will allow us to do full MG sweeps. And then on each level, we'll do use a Chebyshev smoother with Jacobi preconditioner, and on the coarse space, so that's this section, which defines smoothers. And then we can specify in the coarse space exactly what solver we want. So in this case, we'll just use a direct solver LU with mumps. And looking at, so we can just explore that. So as you can see, conjugate gradient, Kulos subspace solver, precondition type is full MG, but now the type is full. And then on the coarse space, you see we've got the LU direct solver and all the information you got from mumps, as you saw in the first set of options. And that takes just over 20 seconds on my local machine. And again, we're solving to within the same tolerance, but we've gone far faster in this case. Now, if we look, so we've done also done a strong scaling study off the on ARCHER2, and you can see that actually, if you use the full geometric multigrid, we do fairly well up to across 2 nodes. But beyond 2 nodes, what happens is we get killed by communication. And the reason this is happening is because the multigrid refinement means that on the coarsest grid, the problem we've got is actually small enough that it could easily be solved on 1 node or even less. But because we've distributed our problem over many nodes, we have to do a lot of communication between the nodes to solve the coarse-based problem. And one way around this is to use telescoping. And this is what this plot here shows, that if you use a telescoping solver, which is this purpley blue line, you can strong scale much better. You can also see that the algebraic multigrid is scaling incredibly well also, but as has been alluded to before, to use the algebraic multigrid, you actually have to be able to construct the finite element matrix, whereas with geometric multigrid, you can get away with using these matrix-free operators. And actually, if you increase the problem size from this strong scaling plot, you find that you can't run AMG anymore because the problem doesn't actually fit on the nodes. So finally, the set of PETSI options for the telescoping are outlined here. So we've got pretty much exactly the same as before, but now on our course level, we're going to use Python. The very first thing to point out is we're now using the matrix-free mat type, which means on our course level, we actually have to use a Firedrake assemble PC, which will assemble on the coarsest space the operator, which allows us to use the telescoping preconditioner inside, as well as the direct solver on the telescoped matrix. So what telescoping does is it allows you to solve the coarsest problem on each node separately, which completely avoids the communication bottleneck, which causes us to strong scale badly. And as you can see at the end here, on 1 core at least, we don't expect any real performance gain because we're not using multiple nodes, but over several nodes, you'll see that the runtime will go down. I'm just sorry, I glossed over that bit there. So we can see here we've got the conjugate gradient KSP object, full multigrid as the preconditioner. And then on the core space, where has it gone? We've got the Python preconditioner, which is the Firedrake assembled preconditioner. And then inside that, somewhere we've got, the preconditioner type is telescoping. And within that, we've then got the LU direct solver. Right, so that was a bit of a whistle-stop tour through all the various considerations you have to make on HPC. And these will affect your solver options and the way you solve the problem on larger and larger problems. So there's a little bit at the end here we've got is directly related to running on ARCHER2. So we've given you an example job script here. We've actually provided one on the machine, so you don't have to copy this code anywhere. You can just move it from the folder. But there's a bit of information here. So this is how you specify your job script. We've already pre-packaged a Firedrake install on ARCHER2 that will automatically expand if you use the job script provided. So you don't have to worry about installing anything. And then you can specify the number of nodes for your problem, the amount of time. You don't need any more than 10 minutes for any of these exercises today. So there's no need to change that. And then you run your Python script, which we've called HPC demo in this case, and we use srun to execute that on as many processes as you have selected. So if you call that job script jobscript.sln, you submit it on Archer with sbatch and just the name of the job script. To have a look at what your job's doing, you can query the queue and have a look for your user where your job is and whether it started, whether it's running. And if you've done something wrong and you need to cancel the job, the sbatch command returns a job ID, or the sq prints it, and you can cancel it with scancel. So we've got an exercise at the bottom for you to complete on ARCHER2. So we'll just walk through very briefly how you do that. Since there's a lot of you here, we're going to specify one grid size to solve on. And I was trying to think, how on earth are we going to split this up? I don't really want to make a table. So if everyone imports NumPy and selects a random integer, and you do whatever problem is in that column of the table, I think that's the fairest way of dividing things up. And if you work through the exercises and you submit your answer at the end, we can actually complete the last part of the exercise as a group. But I'm going to quickly now switch to ARCHER2. So I'm going to use VS Code. I'm not very well versed in VS Code, so you'll have to bear with me a little bit. So you can connect to, oh, why can't, no, give me one moment. So if I press F1, I can connect to a host. You should have, I can't see anything, defined, if you're following along with VS Code, a machine which is login.archer2.ac.uk. And I have many accounts on ARCHER2, so I have to connect with a slightly different one. I'm going to just pause the share whilst I enter my credentials.
So conservative.
Yes, Jack, why aren't you sharing your username and password with the group? And I think that is now connected. Can everyone see this window?
No, we're seeing your welcome window because you shared the window and popped up a new window.
Yeah,
yeah.
Can everyone see this window now?
Yes.
Excellent. Right. So this is on ARCHER2. I can prove it. So this is the login node for ARCHER2. And you should hopefully see my home space. So one thing, hopefully this is the same window and you can still see it. It's doing visual code.
Still got that.
Excellent. So if you type pwd, it prints the working directory. And the first thing to note on ARCHER2 is that if you're in your home directory, this isn't available on the compute nodes. So the first thing you're going to have to do is change directory with a cd command to work / the project code, which for this is TAO34, followed by the same code again, followed by your username on the machine. So for me, that's TAO34 and my initials. For you, it's whatever you signed up with for your on-safe for your Archer account. And then we've provided some template files for you to use. So if you use this command here, cp recursive, and copy this entire directory to your workspace. I think I've already done it. Or no, I haven't. So I can do it now to demonstrate. and there should be a Firedrake HPC demo in there. And in there, we've got all the scripts that we used to create the notebook that you see on the cloud service, but also some template job scripts for you to run. So if I have a look in here, you'll see there's the previously mentioned HPC demo, and you can open that on VS Code, and you see, hopefully you recognize the code that you saw in the notebook, and all the solver options are there, but there's just one solve at the end. So it's up to you to choose the appropriate solver for the problem size that you have. And you also have to change these values to make the correct problem size as well. And in addition, we've provided a reservation job script, which will allow you to use the reservation that we've put in for this afternoon. So you can go ahead and use that. There's also another job script in there for after today's session that will work, but it doesn't use the reservation that we've put in place. You shouldn't need to change much more in here other than the number of nodes that you use and the number of tasks on each node. So hopefully you've all assigned yourself a problem size. If you want to work on the biggest problem size, I recommend going to a breakout room and discussing with one of us how to set up the biggest problem. We didn't sort of advertise at the start, but the biggest problem in this exercise, you'll be solving a Poisson problem with over 1 billion degrees of freedom, which I think should have been the tagline, 0 to 1 billion degrees of freedom. But yeah, if you want to have a go at any of these, one of these columns in the table, and if you get stuck, feel free to message. So we'll be hanging around and we'll just spend the rest of this workshop working through this exercise. But as I say, you only have to do one problem size and we'll collate the answers at the end to produce the convergence plot. That's my home space someone's trying to access.
Yeah, so instead of TA034JDB, you should have whatever username you specified for this project.
Yeah. It's the bit that comes before the @ on the login prompt, if you forgot. In fact, I can share my screen again. So yeah, you want to, so my username is TA034JDB, and it's the bit before the @ on the prompt. That is, yes, another excellent suggestion, type who am I. If you're having an existential crisis on any remote machine, you can type who am I. I haven't been checking the breakout rooms, actually.
I don't think anyone's joined any recently.
Okay.
It's an important piece of wisdom from David there.
Yes, very useful. It's also very useful that that particular reservation if you want an interactive session. Okay, so the values of nx and nref will define the size of your fine grid. So you want to choose nx, and that will define the size of your coarse mesh, and then nref will define the number of refinements you do on that coarse mesh. So if you start with an 8 by 8 by 8 cube, and you do 1 refinement, so that's nref equals 1, it will double the number of cells you have in each dimension. So you'll end up with a 16 by 16 by 16 fine mesh in that case. And likewise, if you start with nx equals 8 and you do 2 refinements, so nref is 2 you'll end up with a 32 by 32 by 32 fine mesh. And I think I called that N in the problem, capital N. These also aren't unique as well, so you can choose the number of multi-grid levels you want to use for a given problem size. That
is correct. And N is 64 is NX is 8 and NREF is 3.
Yep.
Because that's 8 squared.
So Alexander's asking how to edit them. So are you using the Visual Studio Code?
No, at the moment I'm just accessing it from the terminal. I'm not. Did I need to use?
Oh,
I don't have Visual Studio.
No, that's fine. Are you comfortable using Emacs or Vim?
I can't. Probably not. I haven't heard of them. But
or Nano
okay.
Maybe.
Nano might be the friendliest of options. It gives you all the commands at the bottom. I can quickly demonstrate, but you type Nano followed by the name of the script you want to edit.
Okay.
And that will drop you into an interactive editor, but in the terminal.
Okay, yeah, that's fine, as long as I can see what's going on.
Yep.
Then at the bottom, it will tell you what the various commands are. When it has an up arrow, a caret, it means control. And basically, there's only 2 commands you'll need, which is this command to save is command W for write out. Oh no, command O for write out. It's not
Okay.
X. And then command X, I think, to quit, but it's written at the bottom. Control, not command. I'm too much of a Mac user.
Oh yes, I've pre-configured my SSH so it uses the right account for each one. So there might be a bit of confusion there. No, your home directory is empty by default. But you want to change to your work directory anyway, otherwise the problems won't run on the compute nodes. So that's the let me just share my room, share my screen again. So this is where we change to work. Then these 2 project codes will be the same, but this last bit will be your username.
Do you want to run one, Jack?
Yeah, I can do that whilst we wait. So
maybe not the big one.
No, so if I open up the reservation, I can see I've got 1 node. The time limit is 10 minutes. And I'm going to use all 128 cores on that node. And the demo by default is set up to do 8 with 2 refinements in degree 2. So I'm going to double that. Let's do 16 on the course mesh as just an example. So this might not be the optimum set of multi-grid levels, but this is one option. So that changes it in the course mesh size there. So I'll save that.
So for the person who posted earlier, that's an alternative way of doing 64 by 64 by 64.
Yep. And then what I can do is I can type in sbatch. So this is what it says in the notebook, sbatch. And then I called it reservation jobscript.slm. And you can see it gives me a little number back. So that's the unique ID for that job. If I type SQ, and I'm going to put a slightly different option. I'm going to put R, and I'm going to put in the name of the reservation so I can see everyone else's jobs as well, see if anyone's actually successfully running anything.
Oh, look at that.
Yep. So you can see my job is there pending, and someone's got a job in there that's already running on 1 node, which is excellent.
Larissa, I'd guess. So one thing to notice is that no changes were made to hbcdemo.py to run in parallel. So all of the discretization code parallelizes automatically. It will just split itself on whichever communicator it's run on. You do sometimes need to change solver options because there do exist solvers that don't run in parallel, or solvers which have to be configured differently in parallel. That's out of our control, let's say. another one of these. I can't make maths go away for you.
One thing I didn't really... Oh, go on.
You can also, if you wanted to run an ensemble of jobs at once, you can split your communicator, and then you can pass the communicator into the mesh. Then everything that's built on that mesh will be on that communicator. And so you can have a whole ensemble of things running at once. And in fact, there is some convenience functionality in Firedrake called ensemble parallelism, which will you can use to set that up for you.
So one thing I didn't really cover is where does all your output go? So once your job script has run, you type ls, you can see there'll be a little file called slurm followed by your job ID .out, which will contain all the output from that script. So if I have a look in my side pane thing on VS Code, then poke it, it doesn't appear to be there because it hasn't in the right place. Yes. So I can't open it because VS Code can't see it for whatever reason.
You can nano it, maybe.
Yeah, that's a good point. Or I can cat it.
Yeah.
Cat. So this is just so we can see what's in that file. So you can see there's a lot of setup at the start where we load the Firedrake environment for you. And then if I go to the
does 21 seconds seem sensible for the 128 cubes job? How much did you run it on? Oh,
that's not
by
good.
virtual linear solver.
Oh, I think can't remember what I set the default to be.
Oh yeah, you didn't. So you didn't give it any solver options, right?
Ah, yes. Well, that would make sense. Yeah. So you do have to change the solver options. We haven't done
Johnny Bolton. So if you have 2.14 million DOFs, the rough rule of thumb is Firedrake will basically scale down to about 50,000 degrees of freedom per processor.
Yes.
So,
but that's just a minimum. So you can each
so
processor can do a lot more.
Yeah, if you said 100,000 or 200,000 per processor, you'd be on 10 processors, 20 processors for. You can also run it over scaled. It's just it won't go faster. So Amin Rafier, yes, you need to copy the, can you show your screen again, Jack, to show where he needs to copy from?
Yes, of course. I did put the, let me paste it. I think it's still in here. Yeah.
Also, I mean, it works better if you message everyone because at the moment, only I'm seeing your messages.
Yes.
Larissa put it in the chat, I think, as well.
Yeah, sorry, I just sent that as a direct message as well, accidentally. Yeah. But yeah, that's the command.
I mean, just like you were saying that the solver options are a bit of an experimental art. The number of processes is experimental art in some sense. You know, you need to try. I mean, try a sensible number, then try twice as many, half as many, and see whether it's going faster or slower or something. But you may get a hit as you go beyond 128. So you don't need to know what the ARC, but it is important to know that ARCHER2 has 128 CPU cores on each physical node.
Yes.
So 128 processes aren't going over the network. It's just like a very big laptop. But beyond 128, you're on multiple nodes, you go over the network. Although the network is good, you do see that effect potentially. But 50,000 sounds quite good. That a few tens of thousands is the standard numbers I hear people, not like I've heard people saying around. That's per core, sorry, is a sort of a.
Yeah, so I mean, obviously it depends a lot on what you're doing. The actual operator, so applying a one form, so doing a matrix free matrix vector multiplication scales much better than that. But we tend to either run out of what the solver will do at about that level, or we hit some of the symbolic overheads in the Python. And we are currently, there is a PhD student who is currently very aggressively attacking that particular problem. So it currently, so getting through a symbolic operation in Firedrake currently takes kind of a millisecond. and it ought to be able to take tens of microseconds, and we are on that case, which should make that bit a bit better as well. Jack, are you changing your solver options to something that might converge?
Yes, let me do that now. So I'll share screen. So let's try a bigger one. So I can't remember what I think 256 is the second biggest. I won't ruin the fun for.
Why don't you get the one that you submitted to actually work?
Yeah. Okay. So what are the options at the minute?
What didn't it like about the?
It didn't converge.
Didn't converge.
Oh, okay.
So
Going
it
into
ran perfectly happily, but wasn't given a.
Okay.
So I might actually be looking at a different copy of the script in the editor as I'm running.
Does VS Code have some list of suffixes it displays and other ones it does not, something, I guess?
Quite possibly. I'm not a VS Code user normally. So that should have been using the map-free telescope options, which is slightly concerning.
Do you want to? I'm suspicious because I don't think that VS Code does that. To me, it looks like that is a work subdirectory of your home directory.
Yes, but I've linked that to the work directory just as a shortcut, so I know I don't have to type in that big long string.
Okay.
So if I no. Oh, wrong place.
No, going up won't.
No, I went up too far.
I think it's using the right one.
Yeah.
Really? So if you just go into that directory, just go into the one you think you're running in and cat the demo file. See what it says it's doing.
I think it's on. Oh yeah, yeah. Yeah.
Okay. Well, do you want to run one of the other ones then? I mean,
Yeah, let's try
we'll
one.
run whichever one you tested.
Yeah, let's run the one without the telescoping, just FMG.
Did you install your own PETSI, or are you using the system PETSI?
No,
we had to install our own.
Because yeah, I don't think it has all the
Right.
mumps and hyper plugins. Yeah.
But yeah, Firedrake has quite a long list of additional PETSI dependencies that basically means that you need to have done a special one.
Yeah,
if you are installing Firedrake by yourself at home, then the default behavior of Firedrake is to build PETSI with all the right things in it. If you are building PETSI on something like an HPC machine, that is less likely to be a good idea, but you can pass an option to the Firedrake installer and it will simply print out all of the PETSI options that you need, your PETSI configure options you needed. You can add them onto your PETSI configure options list and build PETSI that way. So that's
Also
now in the queue.
Yeah, the system PETSI doesn't have 64-bit indices, which are needed for a billion degree of freedom problem.
That possibly is something that should be reported back to Archer, because I imagine that many people who use Betsy on Archer did want to use a problem that big.
True.
Yeah. Which, I mean, I mean, this is it's gone on for longer than we expected, but this is a sort of interim system until we move to the big system. So some of the things aren't set up as well as they should be, and things at the moment. But
the plan. So Jack will be working on Firedrake on Archer and other big machine stuff on an ECSE starting in a couple of months' time, and the our intention is to essentially roll out what you're using here. So to have a system whereby we periodically, maybe every month, maybe every 3 months, release a bundle onto Archer, which is a setup of Firedrake that anyone can run.
There we go.
Way.
We'll gloss over the bit where I've messed up the the solver options. But yeah, so there's an example. So the runtime there was just shy of 9 seconds for a problem with, it says at the top. Oh, I forget that mumps also spews out information per rank if you leave the SNES view on. So there's quite a lot to scroll through.
Johnny Bolton has a solution.
2 million degrees of freedom.
Invalid account or account.
Are you using the reservation job script or the job script for that one?
I thought it worked. The reservation one worked out the box for me as well, because
yeah, if you use the reservation job script, we've got the reservation details last week, and we programmed that into the reservation job script.slm. We've also included the job script.slm in case you want a template one for after this session. So your account on ARCHER2 will remain active for, I think, about a month after this tutorial.
Okay, but Johnny, I don't think any of the scripts should give you an incompatible account or whatever, which is a bit weird. That would have been true on Archer, but on ARCHER2 it has sensible defaults. Should have sensible defaults.
Yeah, make sure the account's set to the TA034 and not your username. So it's not your user account that you put in there. That was a mistake that I made. Show again how to submit the job on HPC. Yeah, that's fine. So you just type sbatch followed by the job script name, but I'll just do a quick demo there. So I can't see the chat, but if you, so if I type ls at my command line, I can see that I've got this reservation job script.slm, and I type sbatch. So let me just show you what's in the queue first. So you can see there's only one job in there at the minute by AGS. And if I come out of that, if I do sbatch and then the name of the job script I want to run, which in this case is reservation job script.slm, I get my job ID back, and I take another look at the queue, and I can see that job is in there now. So that's my user there, pending to be run. Someone's gone for the big problem, 10 nodes, which is excellent.
Maybe I've done it wrong then, because it's not the big one.
So 10 nodes would be 1,000 processors. So you kind of want to have 100 million degrees of freedom in your problem for that to be a sensible thing to do.
Okay, so how many nodes is it per processor?
So if you're following through the exercise, if I stop showing there, and you've computed the number of degrees of freedom, the maximum number of nodes you should use is the number of degrees of freedom divided by 50,000. Sorry, the maximum number of cores you should use. Sorry, yeah, that was a big mistake there. The maximum number of cores you should be using, so that is a number of MPI ranks, is your number of degrees of freedom divided by 50,000. And then you divide that number by 128 to get the number of cores you should be using, nodes you should be using.
Or in my world, by 100.
Yeah.
Thanks.
Done that one.
So is 10 our entire reservation? Is that why everything was being held for that?
No, we've got 20 nodes. We didn't get the 30. I realized I put the reservation in a long time ago. I tried to put a second reservation in last week, and I was told I already have one.
That's fine, but then I don't understand why those were being. I didn't. The messages that were coming out about things being held.
I think they just held initially, but we do have the reservation. It says your job is being held for a reservation, and then it works out that it's being held for the reservation we have.
Yeah, it takes of order 10 seconds to troll the to troll the queue. So yes, it gives. In the interim, it gives it. I got incorrect things saying that you don't have access to reservation, but it hadn't got around to checking yet, and then it did. I can't remember how you list the. Does the reservation show up? And I'm not. I've only recently started using the reservation in the
Jack, what do we actually, the time that comes out, what is that, the solve time, or is that?
That's just the solve time, yeah.
Good.
So it does take a lot more time, because on ARCHER2, what we're doing is we're unpacking a Firedrake install to the compute nodes. That's saves you, each of us individually, having to install Firedrake in our own user space, which takes a significant amount of time. So we unpack that on the compute nodes, and then it's a pre-baked environment for you to run your Firedrake scripts in. What's more, that environment will be available to you after this session, and even after your account is gone, that link will still work. We won't be updating the install in there, so it'll be Firedrake as it was mid-August, but we intend to improve the installation procedure on ARCHER2 anyway.
So something else that's going on there is one of the reasons why this copy out to the nodes process is done is Firedrake runs in Python, and Python does something very nasty, which is, in order to know where to load modules from, Python on launch, when Python init is called, stats every file in its Python path. That means that if you put something like Firedrake on a shared file system and then run it on lots of nodes, the file system gets very, very unhappy on launch. So you can easily make Python init take an hour or more to run, and also ruin the experience for everyone else on the supercomputer at the same time. And so instead, what we do is we copy the environment out to local storage so that the Python is only touching local storage out on those machines, and we get a fast launch and we don't destroy things for everyone else. And one of Jack's jobs in the ECSE is going to be to roll out something which does that more generally. Oh.
So Mohammed's got an error. I think you just didn't run on enough.
Yeah, Mohammed's got yeah, he's got too big a problem in this case. So you need to throw a bit more compute at the problem size you've got.
The open BLAS error is spurious. I think that's a problem. But yeah, so there's no you have a 256 gigabyte per node minus some overheads, and jobs that exceed that are killed because there's no swap space or anything like that.
Oh, Roberto, the difference between the job script and the reservation job script is in the metadata at the top, where it tells it to use the reservation that's live for this.
For the next 5 minutes.
Yeah, for this exercise.
Yeah, because the reservation is only till 5 o'clock today, but after that you can still run these scripts, but you'll just need to take out the reservation line.
And it will take longer to get through the queue.
Yeah.
Although the short on up to 8 nodes, yeah, the short queue is your friend.
Yes, definitely. Yeah, there's plenty of documentation available, great documentation available on the ARCHER2 website for actually which queues you should be submitting relevant jobs to. So I haven't been monitoring the chat too closely. Has anyone actually managed to successfully run the a given problem size? If you have managed to successfully run it, if you put the size n and the error in the chat, we can attempt to live code a plot.
We've got n is 64.
Nice. Well done, Johnny.
Excellent, excellent.
I should warn you, I will have to leave promptly at 5 because I have to go and collect my 3-year-old from the Imperial Nursery.
So you guys actually at work, in an office and everything?
I am physically in my office at Imperial. You can see out into the corridor over there. So it's morgue-like. There are very, very, very few people in this building.
We've got n is 128 as well.
Oh, nice.
Excellent. I'm just doing is going to copy the code that I had before to a notebook so we can do this quickly.
There's also one that's n is 64, but potentially a different choice of nx and nref.
Is the error roughly the same?
The error is the same, and the runtime is a little bit quicker.
Ooh, excellent. That's what we like to see, experimenting with the different sizes.
Johnny, please could you post what choice you have so we could compare?
I had the same ones.
Oh, the same.
Oh, that's bigger than I would expect for jitter, but anything is possible.
Interesting.
I'm not sure if I've got the right number of. I've gone for 1 node and 40 processes. I don't know that's
Yeah,
right thing. I don't know. I'm a bit confused with the nodes processes thing.
so how many degrees of freedom is that problem?
So 2 and a bit million, 2.1.
2.1 million. So you're pretty close to the strong scale limit, maybe. Igor, how many processes did you use? You used 1 processor. Oh, 128 processors. Okay, so that's an example. So Igor has used 3 times as many processors as Johnny and has gone 1/3 faster, because 128 processors really is too many for 2 million degrees of freedom. That's a really clear example of going over the strong scaling limit.
Interesting.
We've got 32 as well. Also on 128 processors.
Excellent.
Runtime 30. So
that's the same number of processors, but an order of magnitude fewer degrees of freedom.
yeah, it might depend also on what the solver options were as well.
Yep.
And also how you got to the NX is 32.
Yeah, because that's only the course grid size, the NX.
Oh, and SARS has NX 64 NRF2, so that's a big one. That's 256.
Nice.
512 M. So the runtime's quite a lot longer there. How many DOFs is that one?
That one is, well, take a look in my solutions folder.
Million.
So I've got a bit of a Blue Peter. Here's one I prepared earlier because I feared that we might not.
16 million times 8, I think, is what that would be, right? So that's 100 million degrees of freedom, 135 million. So at that level, 500 cores is probably a bit few, right? So that one would probably go faster with more cores.
Potentially.
Okay, it's 1701. I'm going to have to leave, or I will be flayed alive.
So I'm gonna do the Blue Peter. Here's one we prepared earlier. So here's a table of values that we use to perform. Bye, David. To perform these experiments. So you may well have had different choices for NX and NREF, but hopefully you ended up with the same number of degrees of freedom in each case. And this is the number of processes we run in each case and how many nodes we run on, and the H and the error. And right at the bottom, we've got our convergence study. So you can see we've got approximately the right rate of convergence there. So
was that,
go on.
Sorry, was that error the diff with the analytics solution, or was that error the CG or the solver error?
This is compared to the analytic solution. So this is doing the error norm of the computed solution with the analytic solution.
Right.
So yeah, if people are interested, I will put the folder with the solutions in that same shared space that we had before, if you want to have a look at how we did it. But otherwise, I think that sort of wraps up this training session. I think we're going to stick around to answer any additional questions that anyone might have. I think all it remains for me to do is thank everyone for who's helped out here. So everyone from EPCC who's made this course possible, all the people who helped deliver the training, so Koki, Joe, and David, and everyone for attending and participating in the tutorial. So yes, thank you very much. I'm going to stop the recording there, and we're going to stick around and answer any other questions.